Next, Kyungwhoon Cheun, Corporate President and CTO of DX Division at Samsung Electronics, will now deliver the opening remarks.
적인 도구로 자리 잡았습니다. 그리고 이제는 한 걸음 더 나아가 에이전틱 AI 시대가 본격화되고 있습니다. 스스로 사고하고 행동하는 에이전틱 AI, 이것이 바로 오늘 우리가 논의할 주제입니다. 이번 포럼은 에이전틱 AI 시대로의 전환을 맞이하여 이를 가능하게 하는 기반 기술과 실제 제품 및 서비스에 적용된 사례를 공유하는 자리가 될 수 있기를 바랍니다. 에이전틱 AI의 핵심은 크게 두 가지일 것입니다. 첫째는 복잡한 문제를 단계적으로 분석하고 해결하는 고도화된 추론 능력입니다. 이를 통해 AI는 단순한 모방자를 넘어 복잡한 문제를 스스로 해결하는 자율적 주체자로 진화하게 될 것입니다. 에이전틱 AI의 두 번째 핵심 기능은 다양한 도구를 능동적으로 활용하여 그 기능을 확장하고 실제 작업을 수행하는 도구 활용 능력입니다. API, 웹 기반 서비스 또는 로컬 앱 등의 소프트웨어적인 도구 활용을 넘어서 로봇, 스마트 기기 등을 통해 실제 물리적 환경에서도 작업 수행 능력을 갖추게 될 것입니다. 이 두 축이 결합된 에이전틱 AI는 우리 일상과 산업 현장에서 복잡하고 다양한 작업을 자율적으로 수행하게 될 것입니다. 삼성전자 역시 이러한 시대적 변화에 발맞춰 사용자에게 실질적으로 도움이 되는 AI 기술을 준비하여 새로운 가능성을 열어가고자 합니다. 오늘 기조연설에서는 이 분야를 선도하는 세계적인 연구자들과 함께 에이전틱 AI의 기반이 되는 추론 기술을 포함한 미래 AI의 핵심 주제들을 다양한 관점에서 논의할 예정입니다. 이어지는 오후 세션에서는 삼성이 진행하고 있는 최신 AI 연구가 실제 제품과 업무 환경에 어떻게 구현되고 있는지를 구체적인 사례와 함께 공유드리겠습니다. 제품 측면에서는 카메라에서의 AI 기반 화이트 밸런스 기술, 스마트폰 기기에 최적화된 on-device LLM 모델과 개발 환경, 그리고 음성 합성, 자동 자막 생성과 번역을 결합한 새로운 음성 AI 기술을 통해 사용자 경험이 어떻게 한 단계 진화되는지를 보여드릴 것입니다. 생산성 측면에서는 여러 에이전트들이 협업하여 방대한 지식을 탐색하고 관리하는 멀티 에이전트 orchestration 기술과 문서 전체를 멀티모달로 이해하고 구조화하는 다큐멘트 AI 기술, 그리고 실제 업무 환경을 기반으로 설계된 새로운 생산성 벤치마크를 소개드릴 예정입니다. 기존 벤치마크로는 검증하기 어려웠던 실제 업무에서의 응답 품질과 다국어 성능을 종합적으로 평가하는 최초의 시도라는 점에서 의미가 있습니다. 그럼 이제 조셉 곤잘레스 교수님의 첫 기조연설을 시작으로 이번 포럼이 단순한 지식 공유를 넘어 AI 기술의 최전선을 탐구하고 새로운 미래를 열어가는 의미 있는 자리가 되었으면 합니다. 감사합니다.
Next, we are pleased to invite our keynote moderator, Joohung Lee, Corporate Executive Vice President and Head of AI Model Team at Samsung Research. Please welcome Mr. Lee to the stage.
안녕하세요.
Good morning, ladies and gentlemen. I'm Joohung, EVP responsible for AI model at Samsung Research. In this session, we are going to be joined by 5 eminent scholars from abroad, and they are members of the Samsung AI Adversarial team and giving us a direction for future research. Through today's presentation, they will be sharing their in-depth insight. Each presentation is going to deal with a very interesting and intriguing theme. So let us start now.
Let's Welcome the first keynote speaker, Professor Joseph Gonzalez from University of California at Berkeley.
Hi everyone, hopefully you all can hear me. Thank you for having me, I'm excited to be here. So today I'm going to talk about our work in advancing agentic intelligence. So my name is Joseph Gonzalez, and I live at the intersection of two very much colliding worlds as both a professor and an entrepreneur. As a professor at UC Berkeley, I'm one of the co-directors of the Sky Computing Lab. We're developing the next generation of advanced AI systems. And I'm also a member of the Berkeley AI Research Group, or BEAR. We're developing the next generation of AI technologies, algorithms, and models. I've been fortunate enough to be part of some really exciting projects at Berkeley. My students launched some of the first chat-enabled models with the work on Vicuña. And then building on those models, we launched the Chatbot Arena, which is one of the most widely used open platforms for model evaluation. More recently, we've been thinking about tool use, and the project Gorilla has been looking at how we both discover and invoke tools to find the right APIs to accomplish complex tasks. And building on that, we launched the Berkeley Function Calling Leaderboard, which has become the standard platform for evaluating function calling capabilities in models. My group also did pioneering work on the design of agents, and in particular, how we bring memory subsystems into agents to allow them to have long, complex conversations. And today I'll talk a little bit about some of the work we've been building on top of that project. More recently, my group has been focused on the design of systems around post-training that is supporting supervised fine-tuning and reinforcement learning to enable reasoning models and other kinds of behaviors. And so these technologies made it easier for us to develop new kinds of model add-ons or new model capabilities. And then at the system level, my group has been developing the open systems for serving models. From the projects like SGLang and then more recently VLM, we've built the standard tools that people use to serve open source models across many industries today. As I said, I'm also an entrepreneur. I'm a co-founder at Run LLM, where we're building the next generation of AI support engineer agents, so developing agent technologies. I'm an advisor to Genmo, a company building open video generation models. I'm also advisor to Leda, which is a company commercializing our work on MemGPT to enable more stateful agents. As part of a collaboration with my colleagues at Run LLM, we've been writing a blog series called The AI Frontier, which I have a QR code here, and I highly recommend. We have written over 100 blogs. In fact, last week was our 100th blog, looking at the intersection of AI, product design, and how we build technologies and take them to product to industry. And the last blog looked at the evolution of what we predicted would happen and what's evolved in the past several years. So today I want to talk about the rise of AI-powered agents. So for me, agents are AI systems that combine reasoning and tool use to accomplish complex tasks. At the simplest, we can think of it as an LLM interacting with some software services or systems. Though increasingly, it's also interacting with data technologies through things like RAG to find the right information. And as we move forward, we start to think about things like context management systems that manage the memory or context that's exposed to the model. And then very recently, there's been a lot of excitement around being able to build specialized models using all of this post-training work that can adapt to specific domains, have specialized capabilities. And today, I want to convince you that there's significant opportunity for innovation on the right side of this picture, that we don't all have to be developing the core foundation models, that in fact, a lot of the exciting work and maybe the really disruptive work in research and in industry will come from this yellow box. So today I want to talk about 3 exciting efforts from my group. These are relatively new efforts. The first is on sleep time compute, and this is allowing memory agents to reflect on conversations between interactions, enabling reasoning between invocations, between test invocations. The second 2 I want to talk about aren't even published yet, so these are work that's ongoing, will hopefully be on archive in the next few weeks. The first is user agents, and this is learning human preferences by learning to anticipate what a user will say. In a sense, building a digital twin. And the second is advisor agents. This is learning to guide black box models through complex tasks from reward signal. So let's start with sleep time compute. So again, this is joint work with colleagues at LEDA. And many of you have probably already heard about some of the excitement around test time compute scaling. The idea that using more tokens, I could build a richer context that could allow a model to answer a question more effectively. And this has been a big boost to what we can do with AI, but it's expensive and it increases latency between when a question is asked and when an answer is given. So we started to wonder if we could get the benefits of test time compute without the limitations. And our key insight as we think about this is the idea of background inference, being able to reduce latency and cost. And we do this with what we call sleep time compute. So it's bringing in mechanisms to leverage computation before and in between interactions. This allows us to anticipate requests and compute useful quantities before the query ever arrives. And then if we get many questions about the same context, to be able to amortize that compute across queries to reduce cost. So here's a simple depiction of how this works. Imagine you're solving a math problem, as many LLMs do these days. There's often a significant amount of context around the question. The parameters, maybe there's a juggler, the balls, the quantities of things that they're juggling. All of this context is presented up front, followed by a question. And in the normal test time compute regime, you take the context in question, and then you think about it, generating thousands of tokens before you arrive at an answer. In the sleep time compute setting, we iterate on that raw context before the question ever arrives. We compute useful quantities that could then guide the final conclusion at test time. And ideally, we've computed most of what's needed so that at test time, we can only do a little bit of computation to get to the final answer. So let me try to formally describe what's going on with sleep time compute. Suppose we are given a context C and some query Q. The context C could be a collection of documents. The query is maybe a question about those documents. If we look at traditional test time compute, the idea is that we're taking the context and the query and computing an augmented context. And this can be used by the model to answer questions more effectively. And this is an answering step where we then take that final context to produce the answer. The idea with sleep time compute is that we're going to construct this augmented context only using the initial context without the query. And we can reuse this amortized sleep time compute context across different questions. So that at test time, we can take this context, append it to the query, and get a final answer without the need to make another sequential decoding call. So in practice, it allows us to be both more efficient and reduce costs. And we do this using an agentic loop to optimize the sleep time context. And this is building on this memory architecture we developed with the MEMGPT project. And I think this points to this bigger idea of how we manage context more effectively by giving a model tools to allow it to move information out of the conversation into long-term and short-term memory, and then pull those memory facts back into working memory as the model proceeds through tasks. With sleep time compute, we prompted the model to prioritize information over existing memories, to consider how information affects previous memories, and to use reasoning to identify logical conclusions and potential hypotheses. This allows us to scope what we produce in this sleep context to help the model most effectively. So to evaluate this, we developed some new benchmarks extending some of the standard mathematical benchmarks to introduce additional symbolic state both up front and then to reuse some of that state across different tasks to test the scope of what can be achieved. And so when we do this, we can reduce test time compute by up to 5x at the same accuracy, because again, we can do all this pre-processing. We can also increase accuracy by 13% when the budget isn't constrained. So we can do additional computation on top of all this sleep time compute to get further high quality results. And then if we have lots of questions around a similar context, we can see significant reductions in cost, again, by amortizing this context across queries. So there are a lot of opportunities for sleep time compute. I want to highlight some of the important use cases. In software engineering, the context C could contain the entire repository that we're reasoning about. So if we are processing it at sleep time, we could summarize the structure, identify patterns and issues that could help address future bugs or questions. For document question answering, the context contains the documents. And then the sleep time compute could help identify important facts and relationships that we could infer from those documents. And then for long conversations, the context C contains the memory in the previous dialogue. And again, we can think of the sleep time compute as anticipating what might be said, refining our understanding of the previous conversation, and maybe guiding towards an answer that would be most appropriate for the given user. So in fact, the work on this, on sleep time compute, got us to start thinking about user agents and how we might be able to learn how to respond for a particular user based on interaction with that user. So your user agents are allowing us to learn human preferences from interaction. So we think of how we currently learn a preference. A lot of the work builds on this kind of binary comparison of two agents, of two responses. So if I have a response A, a response B from an agent, which one does a human prefer? But if we think about natural conversations with a human, the natural form of interaction in something like unstructured chat, we don't get this binary comparison signal. And so the research problem we explored here is how can we learn this human preference from unlabeled data, from these direct chat interactions? What we've proposed here is unsupervised preference learning through user agents. And again, these agents are going to act like digital twins of the user. So here's a big idea. So imagine one of my grad students is trying to draft an email to me and they have an AI helping them write the email. It writes a draft and they might give some feedback like, hey, make it less formal or more concise. It gets another version and they might say, hey, that looks great. In this conversation, they've revealed preference information about what they look for in an email to their professor. And now grad students using this thousands of times a day, or at least a week, they collect a large number of these conversations for any one user, for any one graduate student. We'd like to be able to automatically extract the preferences from those conversations, in a sense, to build a user model that can answer the question, what do I prefer, A or B? So we sought to make this work using the sort of standard techniques you would imagine in post-training today. Our goal here is to teach a model to complete the user's turns consistent with their given preferences. And we start with something like supervised fine-tuning on user turns. We have all these dialogues, and now we're teaching the model to not respond as the agent, but to respond as the user. And we did this, and it actually is kind of neat. It starts to sound not like a helpful agent, but like a demanding user looking for progress on its problem. But it doesn't yet capture the user's preferences. So we found a way to solve this by augmenting the training data with contrastive examples where when the user gave one piece of feedback, we can synthetically generate other feedback to contrast against, and then use something like DPO on these user turns. So this actually starts to sound more like the user and captures the user's style of responding. But unfortunately, if we do this, the model doesn't yet have the ability to answer questions like which response is better, because again, those kinds of questions are pretty out of domain. So we found a simple solution here. We can use our earlier synthetic data set to then generate multiple responses from the model, and we know which one was created based on the feedback that the user originally gave. And now we can also create some examples of this binary preference signal. So putting all these pieces together, we can build a model that actually can respond like a user and even answer questions about a user's preferences just from conversations with the user. And if we compare that preference scoring, so 50-50 being just guessing, which is what a baseline model would have, and then even against in-context learning where we show some examples of what the user prefers, combining these other techniques, we can get a significant boost in accuracy and our ability to infer the preferences of that user. But maybe more interestingly, we can now simulate a user. So a user might ask for something, the base model can generate a response, and our user model, our digital twin of the user, can provide feedback in an iterative loop before the human ever actually sees the model's output. And then after this iteration process, we can give a much better revised response, again, by simulating human preference. So this work on modeling human preference got us starting to think about maybe there's a way for models to give other models signal to guide them through a process. And so the last thing I want to talk about is learning how to guide a black box model through complex tasks. So we call these advisor agents. And we're going to, again, use these learning techniques, in particular reinforcement learning, to teach a model to help another black box model complete a task. So we think back on how agents learn. There's some flaws in each of the approaches. The standard approach in context learning or prompt engineering relies on carefully constructed prompts and examples to guide a model to address issues to solve a problem. But this is brittle and requires significant manual effort to find these examples and provide the correcting feedback needed for a model to succeed. The other approach, which is pretty exciting, is post-training. We use supervised fine-tuning or reinforcement learning to augment the LM with new behavior and knowledge. But this approach is pretty sensitive to variation in domain. It can lead to things like mode collapse or loss of instruction following or other kind of general behaviors that we need in our base model. So we thought we could try to combine the best of both worlds to use both in-context learning and post-training in a way that preserves the advantages of in-context learning and post-training. So here we're going to use reinforcement learning to train a second, smaller advisor model to adaptively prompt a stronger black box model. The idea here is we're going to retain the original model, the general instruction following capabilities of our black box model. And this could be a state-of-the-art model that we can't even train in the first place. And it's also going to eliminate the need for prompt engineering because we're going to learn to construct a prompt based on the current state of the conversation. So this is a conditional prompt. And we're going to do that from reward signals. To show you what this looks like, I might ask a model, help me write a review for the book Frankenstein. The advisor could jump in and provide additional information. And again, if you think of the work on user agents, that's a kind of an early example of an advisor, giving advice to the base model on what I might prefer. The model generates a response, and again, the advisor can look at the output of the black box model and provide even more contextually aware guidance. For example, provide more historical context, so that the black box model produces a result that's again consistent with the end goal of the user. So to give you an example of how this works, so we have a small open source advisor model, and we're going to use this smaller model to guide our larger black box model. We let the black box model generate a response to some given user prompt, and the advisor model is going to look at that and provide natural feedback and in a sense iterate with that black box model. And when this process is completed, the resulting output, the final outcome, is given to the user or maybe iterated on in a bigger agent loop. And then when a reward is finally computed, that reward is sent to the advisor model. We're unable again to train the black box model, we're leaving it fixed. We are tuning the advisor model to give feedback to the black box model that is more optimal for the reward or the desired outcome. So here the advisor model learns to guide the black box model to maximize reward. And it allows us to preserve the general capabilities of that black box model. And again, this is critical as many of the post-training methods often change how a model behaves, especially in out-of-domain tasks. So early results on this, and here we're going to compare against GEPA, which is one of the other techniques developed from our group at Berkeley, thinking about how to augment prompts using genetic algorithms. Here we're again going to use the reinforcement-based approach, where our advisor is this Qwen 2.57b model. It's a small model. And our black box model, the one we're going to guide with our advisor, is GPT-4o mini. And if we look at three different preference tasks that we created, length, level, and pick versus choose, which are simulating different kinds of latent human behaviors, the advisor is able to very quickly dial in on what is it the user wants, just from a reward signal now, and then use that information to guide the black box model to get to the right answer. So I find this pretty exciting as it allows us to now use reinforcement learning in a new way, in a way to construct prompts or to search the space of prompts or conditional prompts more effectively. All right, so I've highlighted three directions that I think are really exciting and sort of speak to this effort or this opportunity in how we advance the systems around the LLMs that we're building today. And now I want to take a moment to look to the future and talk a little bit about what this could mean as we build these systems, not just for agents, but for humans. So we go back to this picture. I've made this case, I hope, that this yellow box has an enormous opportunity for innovation. And those innovations can happen while we leave this black box, the LLM, fixed. But that also means that I can replace that black box with a human. And in many ways, these same innovations should also help a human accomplish tasks more effectively. So things like agent memory could be there to help a human organize their context, the interactions in a way that is more helpful to the task they have at hand, and then maybe even capture things from their actions to be used in the future. This idea of sleep time compute offers the opportunity to think about recording the past, thinking through it between and before interactions in the future, and then using that additional offline reasoning to really augment what the user is presented when they encounter a new situation. I like to think of, I meet with many students throughout the week. What if the sleep time compute could analyze my previous conversation? So when I get to the first meeting of the student the next week, I have a lot more context that's been enriched by reasoning about the past. We think of user agents. Imagine if we could model ourselves in complex situations. This could not only allow us to simulate how we might respond, but also help us respond to things more effectively that reflect how we as people would encounter or would respond in those situations. And then finally, advisor agents, building models that can then guide humans more effectively from reward, knowing when I succeed and when I fail. I don't necessarily have to learn anymore. I can allow an advisor to provide guidance based on the signals it captures, given the context that I've accumulated. So I think this is pretty exciting for an organization like Samsung, because in many ways, we at Samsung are building tools that interact with our environment that capture a lot of this rich context, both on our bodies and the devices we interact with in the world. And I think that context will be critical to really enabling humans to benefit from many of the advances that we're pushing in the systems around AI. And so being able to read email, messages, audio, video to capture that in a secure way on the device so that all the interactions I have are recorded in some way that I can then process. This opens up really exciting opportunities for things like a memory agent that could surface the right information to humans as they need it. It gives me a chance for advisors or user agents to model how I would respond and also guide me through complex processes, help me achieve my goals more effectively. And things, again, like sleep time compute could run in the background on these devices, allowing the down cycles to be used to really understand my context better, so that when I encounter a new situation, there's significant thought that's gone into my context to help me succeed in that new context. All right, so I want to conclude by saying that there's a lot of exciting things happening in the space of agentic intelligence, and the innovations really in this systems and AI interaction. And I think that will advance AI capabilities, but I think it also really opens the opportunity to advance human capabilities. And with that, I thank you, and I'm happy to take questions at the panel afterwards.
Thank you, Professor Gonzalez. So we are going to hold a Q&A session after the second speaker, but I want to mention that the topics that you bring into is very relevant to Samsung, as you say. So we have a lot of devices and store the user's preference and the context, and how do we compute this maybe during the sleep time, or how to leverage this memory well. This is a very important topic. So we are going to have more questions after the next speaker. So let's move on to our second speaker, Professor Subbarao Kambhampati from Arizona State University.
Okay. Thank you for inviting me for this Samsung AI Forum. I'll be talking about how LLMs reason. It's sort of well connected to the whole agentic systems aspect that we'll be seeing in a minute. For those of you who want to follow along, the slides have actually been posted. So that's a bit.ly link that might come up again. So you can look up there. Okay, so let me start by mentioning that I was here in 2020 for Samsung AI Forum. That was the first of the pandemic ones, unfortunately, because of which I had to do it by Zoom. After that, I've actually done a bunch of things in Korea again by Zoom on various TV shows and so on. So I'm kind of slightly disappointed that I'm again doing it by Zoom. Hopefully one of these days I'll actually come to Seoul. But thank you again for inviting me. I am work in automated planning. My career has been in automated planning and decision making. So the important thing for an agent is what do I do next, given the environment, the kinds of actions it has, the kind of sensors it has. And these can be software agents, they can be physical agents and so on. And most of my life I have spent on actually figuring out how to do planning in under different kinds of circumstances. So that's sort of well connected to essentially agentic systems, because as we'll see in a minute, as basically the agents really have to plan to achieve specific tasks in the real world. And so basically, really, I'm going to be talking more about a particular form of reasoning, which is planning, and how do LLMs plan. And from that, you'll get a lot of interest, connections to general reasoning aspects too. Okay, so in general, I want to kind of make the distinction between being able to act, which is like calling tools, etc., and being able to plan, which is making sure that the calls that you're making are going to be connected towards some high reward for you. If you don't know what you're doing, just by doing actions, you can get into lots of trouble. For a minute, think about leaving a gun lying around in a home with a toddler. The toddler would know how to use the gun, but doesn't quite know what is the right ways or wrong ways mostly to use them. So in general, it's clear that LLMs can essentially do tool calls. One of the interesting questions that we also need to know whether they want to be agentic systems is to what extent can they do planning for themselves? You can actually do orchestration from outside, that will work fine. But the question is, can LLMs also do orchestration themselves, and under what conditions can they do it? And so to do that, actually, we started by basically looking at this, a couple of years back. And then, the general idea there was that people are assuming that LLMs can already do planning. Lots and lots of papers were written before 22 itself. And so the question, of course, is whether that does make any sense, especially these are the standard LLMs. These are the ones that we're talking about where you have autoregressive simple LLMs. These are not even the reasoning models that we'll be talking mostly about today. And the problem with LLMs that some of you have probably realized is they have a huge memory effect. Their intelligence is kind of jagged, so they can do pretty amazing things, such as winning international math Olympiads, but just fail flat on very simple kinds of reasoning. People keep showing this all the time. This is one of the recent ones where they somebody asked ChatGPT 5, Amazon sent me a left shoe instead of a right shoe, and a right shoe instead of a left shoe. What do I do? And ChatGPT gives a multi-step plan trying to send all the shoes back, even though it's obviously clear that the shoes are fine, right? So in general, the fact that they can do well in something doesn't necessarily mean that they can do well in anything else. And this is a big issue because of the memory effect of LLMs. So when you think about autoregressive LLMs, compared to humans, essentially who have both system 1 and system 2 for deliberative reasoning, planning and reasoning tend to be deliberative, LLMs really should be seen as like a huge external system 1 for humanity as a whole. And so the question then is, why would you expect them to do planning correctly? So we actually started checking this a couple of years back, and there's a bunch of papers on this. So for example, in New we basically have this series of 3 papers showing that, if you think of planning as actions with actual interactions, such as something extremely simple, such as stacking blocks on top of each other or doing logistics, it turns out that actually their planning performance is pretty abysmal. And it becomes even worse if you change the names, so obfuscate the domain. We have shown this. And of course, we also shown that other kind of ideas as a chain of thought and react don't necessarily help as much. In particular, chain of thought helps improve performance for the examples that you have given, but as the length of the examples increases, they fall down. So something as simple as last letter concatenation, it starts high enough after you give a chain of thought prompt, but as the number of words increase, it just starts falling apart. So there were papers on that, and NeurIPS 24, NeurIPS as well as TMLR on those things. Should not be surprising that LLMs can't take advice because in a guaranteed way, because after all, as as John McCarthy said, one of the goals of AI itself is to be able to take advice and follow it correctly. And so it's a pretty hard problem. So it should not be surprising that regressive LLMs can't do this. So the question, of course, is then why are people actually at that point of time saying that they could do planning? And it turns out planning has like two really different pieces. One is knowing what possible actions are there and whether you can even make up actions if you can't think of, if you haven't been given those actions. And secondly, making sure that the actions can be sequenced in such a way that they don't run into problems. That means there are no interactions. And if you have played any blocks world kind of scenarios, you will know that the order in which you do the actions winds up making sense. If you want to put A on top of B on top of C, first you have to put B on top of C and then put A on top. Otherwise, it will not work. And in general, interactions is what actually makes that part complicated. LLMs are actually very good at the planning knowledge part, but they're very bad at the interaction resolution part. And we can show this by taking something as simple as blocks world and removing all the preconditions and the delete list so that the actions don't get into each other's ways. And if you do that, actually the performance of LLM, accuracy performance, improves quite significantly. Still not 100%, but it improves significantly. In general, so autoregressive LLMs will do fine if for planning if your domain doesn't have action interactions, and action interactions are connected to what has been called ergodicity of the domain, ergodicity of the world. An ergodic world is one where essentially it's a forgiving world. You can go from any state to any state with non-zero probability. So ergodic worlds don't have death, they don't have accidents. And so in those kinds of scenarios where you can't overwrite files, etc., LLMs actually are fine because the planning itself is kind of less critical. Knowing what actions are relevant are probably more important. Now, that is about autoregressive planning LLMs, and we have written a bunch of papers on that. But as of last year, approximately just about last year around this time, September 12th, 13th, actually, if you might remember, some of you might remember, the Strawberry model, the O1, was released by OpenAI. And the difference between the standard LLMs, which are autoregressive, and the reasoning models is they have these two ideas that I'll talk about in a minute, test time scaling and post-training. And then I basically want you to understand why they help and how they don't help necessarily. That's what I'm going to do. So we, in fact, last year, we spent a bunch of time writing, basically digging into this and writing a bunch of papers, some of which are shown there. But I basically want to walk you through a perspective on how do you go from what was originally a system one for humanity, which is autoregressive LLM, so that it will actually also have sort of system two style behavior, something like reasoning. So that's the kind of thing that we want to understand. How would you go about it? One simplest idea to start from is that think of LLMs as idea generators. They can generate ideas about everything, including actions, including plans. They might give you a suggestion of this could be a plan, etc. And so the question then is, if you use LLMs as the idea generators, then if you have some verifier in the loop that checks whether the idea is correct, then you have a verify, generate, test loop. And the generate test loop is essentially how you start getting guarantees about reasoning from LLMs. And this has basically been called test time scaling. I'll make in a minute. But in general, AI systems, so basically, having the ability to generate ideas from LLMs can be used along with a verifier. So there is a bunch of ideas for test time scaling, including just let's generate a huge number of suggestions for plans and then maybe take the one that has the majority. It's been suggested more times. But a better idea that I like, which especially because it's connected to our work, is what I call LLM modulo, where you use a large language model as a generator and you have a bank of critiques or verifiers that critique the plan from various different angles. And if there is any problem, they will give a prompt back. It's called back prompting instead of backtracking. And this back prompting can be used to come up with a next suggestion from LLM. And then this generate test, if it ever ends, in the sense that if in fact critics are happy or a majority of critics are happy, then you can send the plan out. And you actually will have guarantees that the plan is correct in this case. So one of the questions, of course, is where are these critiques coming from? One obvious idea would be to try and say, let's just use LLM itself as a critique. I'll show you in a minute that verification is, while oftentimes cheaper than generation, computation, Additionally, LLMs are not necessarily any better at verification than they are at generation. We have a iClear paper that I'll talk about in a minute. But in general, there are actually verifiers that might be available for your domain. And so you could use them. You can also learn verifiers. And when you're learning verifiers, you can either learn them as either LLMs, fine-tuned LLMs, or some sort of learned neural networks or something. Or you can also actually have LLMs to generate code for the verifier and have the code checked in a LLM modulo loop. That's a synthesized verifier. So that's also possible. And then these kind of verifiers can essentially be about correctness. Mostly that's what we'll care about in terms of agentic systems, safety aspects. And they can also be about style. And for the style, actually, LLMs are much better because there are no actual classical techniques. But for correctness, you tend to have to either have learned verifiers or the verifiers from outside. If you use LLMs directly out of the box, you can actually worsen performance. I'll say in a minute. So LLM modulo, we have shown in ICML last year that it actually improves performance like significantly from the base LLM. And the more number of iterations you allow between generate test, the higher the accuracy is. And furthermore, when actually a plan comes out, it's guaranteed to be, it has passed the critiques. So this is how actually human experts looking, NASA, human experts looking over multiple mission plan being generated, will all of them say, am I happy or not happy? And then if they stop critiquing, if they're fine with it, then you will say the plan is correct. And so that's the kind of thing that you can do with LLM modulo. And it actually provides some guarantees about the plan correctness. And another important thing to remember is we're not just giving it to some classical solver outside. We are using verifiers. They're actually composable. And in general, solvers are verifiers plus search. And we are letting LLM actually do the generation of the ideas. Okay, and as I mentioned, actually, to the extent critiques have good properties, those transfer to the solutions being sent out, and this is how you can get safety considerations met. As I mentioned, if you actually wind up insist on using LLMs to do self-critiquing, sometimes actually LLMs might very well walk over a correct solution only to stop with a wrong solution because they might actually have both false negatives and false positives. And in fact, in the iClear paper, we show that in several cases, actually, LLMs being self-critiquing themselves worsen actually the performance than LLM just guessing one and then calling it a day. So that's the thing to keep in mind in terms of just using them directly as verifiers. But to use them as style critiques, it actually makes a lot of sense. There's a paper in COMB last year which shows that a vision language model in this case can actually critique a behavior, all of which actually reach the goal, but some of them may be better than others from the implicit human constraint. So for example, in the lowest one, you don't want a robot to give you a pair of scissors with the pointy end towards you. So that's a bad thing. And that's something that VLMs are actually able to capture. And it's much harder to get classical verifiers of that sort, classical style verifiers of that sort. Okay, so that's about test time scaling. And in fact, it guarantees that there's no mystery there anymore. You're just using LLM as a generator, and you're using a verifier to see if any of the generated ones are actually good. And the power comes because LLMs are actually pretty good generators for many, many domains. They don't give up. They actually generate things that are kind of possibly reasonable, and then the verifier makes sure that they're actually correct. But as in fact, one of the problems, of course, in the test time scaling is this is all happening in the user-facing time. And so you don't want to wait. After you hit return, you want answers. So the question is, how do you make sure that this test time scaling, which does work, actually is somehow compiled back into the base model? Marvin Minsky, another of the founders of AI, basically said intelligence is integrating test part of the generate test into the generate part. And that's what we do when you do post-training. One example in this case, for example, is you can essentially take this LLM modulo idea that I had and generate, basically get a large number of problems and then try to solve them. And you have verifiers, they check whether the solution is correct or not. And then you have a whole bunch of synthetic data. Now you can fine tune the LLM back. That idea is basically the start of post-training with the synthetic data, except the real post-training that is actually become more popular does a couple of extra things. One is you not only, you basically not only do fine tuning with SFT, sometimes you do fine tuning with RL, reinforcement learning. I'll tell you in a minute how that changes things. And the other thing is essentially that you also have intermediate tokens rather than just give problem and answer and fine tune. You say problem, a bunch of intermediate tokens and the answer. And these intermediate tokens it's not well explained as to where they come from. It could be humans trying to give step-by-step instructions. It could be like an outside solver essentially giving its data structure manipulations as the trace time, as we'll show it in a minute. And these intermediate tokens with the synthetic data, if you then either SFT or RL, that basically improves the accuracy of the base model high enough that you start having better performance. No guarantees, but better performance. It becomes a better generator. In terms of the RL part, all that actually happens is you have the base model generate K trajectories, K intermediate tokens followed by a guess on the solution, and you have an actual verifier. This is why it's called RLVR, RL with verified rewards. So the verifier actually evaluates the trajectories that end in the correct solutions and reward them. And then you use the policy gradient methods to push the LLM parameters towards the good trajectories. And if you do this long enough with a large amount of synthetic data, then you will start having base models that have higher accuracy, but still no guarantees. There are all sorts of issues as to whether or not RL is doing anything much more than SFT that I'll get to hopefully, but that's basically where RL is. So when I gave a talk back in last August in ACL as a keynote about whether LLMs can reason and plan, that by that time, remember, there's only autoregressive LLMs. Right after that, in September, when this O1 model came along, Noam Brown basically tagged me and said, look, Rav said certain kinds of planning problems can't be solved, but O1 does solve it. So in fact, we did do a systematic evaluation. There was one paper right in that month, and then that was a longer version of that in TMLR. And basically, the answer is yes, reasoning models are better. As I said, they're better generators than the autoregressive LLMs, direct autoregressive LLMs. In essence, they are training themselves with significant amount of extra synthetic data with this, the intermediate tokens about which we'll talk about in a minute. And this accuracy, they do start with a high enough accuracy. Like if you look at these curves, in terms of the plan length, and the lower plan lengths, the O1 performance is quite high. The very top is, of course, the actual Oracle performance, the 100% accuracy. You see that they're much higher to begin with, but then as the length of the plan increases, they keep falling down. So they degrade in performance as the expected length of plan increases. And they're also particularly worse in the paper we show on things like unsolvable instances. The reason why this happens is not that hard to understand if you get the perspective that what is happening when you are doing the RL trace, the way that I mentioned, is that essentially the base model has a top K accuracy on a certain set of problems, and the RL or the SFT makes the top K accuracy become closer to higher top 1 accuracy on that bunch of problems. In doing so, it improves its top K accuracy on the next larger set of problems, larger length problems. And this has to be done incrementally. So basically what you can think of is that the reasoning models are slowly compiling the verifier signal into the generator. It's not a bad thing if you're using the LLMs as your go-to thing and somebody else already spent all the time doing this post-training, but this is really what is happening. It's incremental compilation of verifier signal into the LLM, base LLM. And one of the other things to understand here is in machine learning, essentially people are always talking about in versus out of distribution, and LLMs actually try to shortcut the out of distribution problem by saying put everything in the training data so that there's really nothing left outside. This almost works, except in reasoning problems, because there are essentially, if you take something as simple as last data concatenation, there are infinite number of last data concatenation problems. There are infinite number of block solved problems with increasing lengths and so on. And if you can pick up the algorithm, that's just a simple algorithm. But what LLMs are doing is essentially incrementally compiling longer and longer plans, longer and longer solutions back into the base model. DeepSeek R1 is actually competitive with O1. We show that too. And more interestingly, I think 2 months or 3 months back just before summer, folks in Apple redid these experiments, except with even more, like not just the O1 and DeepSeek R1, but also Claude and various other things. And they basically showed the same results that we have shown, which is that as the length of the plan increases, the performance plummets. You can see this as that's okay. If I don't really like particularly long plans, then I still have this particular model will be fine enough for me. Interestingly, so there was actually much more of a surprise at this for some reason. It shouldn't be surprising if you heard what I'm saying, which I've basically been talking about before too. But then, it turned out that Apple paper kind of got some, people be surprised at the results. And then the New York Times article, which does actually point out that we did this earlier work on that. Okay, one other point is, I said that the performance improves, the generator's performance improves, but no guarantees still. So what if instead of using LLM in the LLM modulo, I used LRM? That means I use O1 or Claude or something, and then put it in a verifier loop to actually generate verify loop, to make sure actually that if you, in fact, safety matters to you, that's pretty much the only way you can get safety critical, plans. And so this we show that this sort of a large reasoning model actually, and one of the interesting things is this large reasoning model now is not only doing post-training, but is again doing test time scaling actually, because you're doing, the verifiers are checking whether the solution you produce is correct or not. And if you combine that with these verifiers, you can get both higher accuracy and actually guarantees that, in fact, what you're saying is correct is definitely correct. Okay, so the TLDR on this basically is that if you're trying to deploy LLMs in agentic systems, make sure that the scenario you're working with is ergodic. Many software tasks, basically tend to have this property, especially if you are not overwriting databases, and so that you can walk the things back if the plan goes wrong. And then, so mostly what you're celebrating is that they can make complex tool calls. Now, that's a reasonable thing to celebrate. If the scenario is non-ergodic, consider test time scaling and verification techniques, either LLM modulo or LRM modulo, and then invest time on providing and or learning good verifiers. The good verifiers are important both for the post-training, which is basically RLVR, which is verifier, which is basically LLM modulo being done during the training time, and also for the outside, because you want to improve, guarantees about, correctness of the solutions that you're providing. Okay, so that sort of is the bigger points I was going to get at. But now I want to talk a few things about some bleeding edge stuff that we're doing about understanding some of the issues around LRMs. One of the important ones tends out to be the intermediate tokens. The second is RL formulation. Let me see if I can get you through intermediate tokens idea. So the intermediate tokens have been thought of as the thoughts. The model gives some thoughts before it gives the answer. And there's this idea that people can read these thoughts and see if the model is actually correct or not. And so it's very important to distinguish between two different roles of intermediate tokens. One is the intermediate tokens. Everybody agrees that the intermediate tokens are, training with intermediate tokens is helping the LLM's accuracy. One question is whether you can interpret the intermediate tokens mechanistically in terms of why the LLM is doing better because of these particular intermediate tokens. The second is, can the users understand these mumblings and somehow do something constructive with them? And the first is fine. The second turns out to be a huge problem. I want to convince you of that. So in particular, why do intermediate tokens seem to improve accuracy? My perspective is essentially that it turns out a right prompt augmentation can always increase the probability of completion happening to include the correct solution. And these prompt augmentations don't actually even have to be understandable to you. It just has to be a series of tokens that LLM makes sense of. And if you remember, LLMs essentially are thinking of all words as essentially points in this embedding space. So in fact, the prompt augmentation can even be from the continuous latent space. And And it can actually, there is work showing by others showing that that sort of a thing can also improve performance of the LLMs, accuracy performance. And you can clearly see that the continuous latent-based tokens won't make any sense to the humans, clearly. Okay, but people think that since the intermediate tokens tend to be in English, some sort of a pseudo-English. In fact, DeepSeek R1 first had DeepSeek R0, which was just essentially doing the post-training with RL. And then they found that it was combining English and Chinese. Then they overloaded it to only produce pseudo-English by doing additional supervised fine-tuning so that it'll only do actual English sort of pieces stuff. And then they basically said that people can now understand these intermediate tokens and they can trust the results well. But that turns out to be a very bad point, because essentially these tokens that they generate tend to be a humongous amount of pseudo mumblings, which actually nobody really tries to, can make sense of. So for example, R1, DeepSeek R1, solving a simple 4 block, in this case, mystery blocks full problem, starts saying the following things as its intermediate tokens are quote unquote thoughts. This is the first page. That's the second page, third page, fourth page, fifth page. So 5 pages of stuff that if you read, it's in English, but it doesn't actually go anywhere. It's garden path mumblings. And what people do is they look at pieces and say, hey, seems to make sense. It says here, aha, here it says, let me verify. So it must be actually doing that stuff. So this sort of should remind you of, if you know, a Rorschach test, where essentially ink blot tests, where people start seeing patterns that they are evolved to see rather than by design, the pattern actually being present. So, but the question, of course, is how do you show that they don't actually have meaning? It turns out that for the DeepSeek R1, it becomes very hard because there's a whole bunch of English. I don't know how to simulate that. So we did this work, interesting work, where we train an A-star search algorithm on a bunch of, we train an empty transformer with a bunch of mazes being solved by an A-star search algorithm. And these mazes are generated from very different distributions. And then you essentially try to see if, in fact, you can try to see if, in fact, this particular trained model, when it produces the tokens, it'll also produce the A-star search like traces, such as creating open list, closed list nodes. And A-star search can simulate those, and then you can see if they're making any sense. We find at first that there is actually no direct correlation between the validity of the trace and correctness of the solution. And that made us think, what if you actually trained the model with swap traces? That means you give the problem somebody else's trace and the correct solution for this problem. So every problem has wrong trace. And if you train like this, you find that this swap trace model still actually has pretty high accuracy. In fact, it has even better out of distribution accuracy. And yet, of course, its plan trace validity is 0 most of the time, right? That sort of tells you that the validity has no connection to the accuracy directly. And then we also show that RL improves accuracy, but does not necessarily have to improve trace validity, especially in the case of these models such as the swap model. And then the last thing that I will have time to say here before I just stop is reasoning length. So the length of tokens is being connected to, maybe it is connected to the problem complexity. It turns out we actually checked this, and by actually taking that transformer trained on real hard mazes and asking it to solve trivial mazes where S and G are both in the free space. And you will see that basically it dies on these problems, and the amount of tokens it generates has nothing to do with the complexity of the problem. In the plots below, the x-axis shows you the actual complexity of the problem in terms of how many steps, how many operations A-star search has to do, and the y-axis shows how many intermediate tokens are generated, and you see there's basically disconnect there. So that sort of makes you think that, and we also saw this in Q&A tasks, and we actually showed that the ones that improve accuracy are not actually making sense to humans if you do human subject studies, and the ones that make sense to human subjects don't necessarily improve accuracy at the same level. There is a bunch of things about RL that I won't have time, unfortunately. It turns out that it's a degenerate MDP formulation, because of which it's close to essentially incremental supervised fine-tuning. And then the increase, people have tried to assume that RL increasing the token length, RL trained models giving longer and longer tokens is an indication that it is actually improving its reasoning. And we show that it is actually because for wrong problems, you will always have much longer traces than the right problems. So that's basically RL improving thing. And so the perils of this is, if you are saying they have meaning and they don't have meaning, then people can actually start trusting solutions that are actually wrong, and that could be a problem. And so there's actually some coverage on this thing. And then I said, if you're deploying LLMs and LLMs in agentic systems, you should be careful about this. They're very useful in some ways, but they're also currently yet they have their interesting, the autoregressive models don't work at all in non-encoded domains. And the reasoning models basically don't necessarily generalize too far, but they do have these issues about intermediate tokens and so on. So I will stop here. Thank you for your time.
Thank you, Rao. So we are going to Q&A session. I will invite both Rao and Joy on the same session.
Excellent.
Okay, so I guess you guys talk related. So Joy was talking about agentic system starting from the LLM and how to build upon that, while Rao is going into the LLM more deeply. So there are some common things between your talks. One thing that I noticed is in advisor model that Joy was mentioning, in a sense, it's kind of prompt augmentation that Rao was saying, right? So, but then this is somewhat controversial question that Rao is saying that intermediate tokens doesn't have to be interpretable and it doesn't have to be the best prompt, right? So how does it actually help, Joy, when you do this advisor model? What is exactly advisor model is doing to the black box model? And
yeah, it's a good question. So what we're doing with the advisor model right now is we're trying to provide more context to the problem. Often it might be learned information about the user that I want to put into the black box model, but I can't because it's fixed. I think Professor Rao's comments are more, and I actually agree with them, that the context generated through reasoning isn't for us. It's tokens that guide the model to success. And as we do RL on these models, they often become gibberish. And people get upset about that, and they shouldn't. The gibberish is there for the model to get to its answer. Sort of like, in your head, there's likely gibberish that gets to an answer as well. We don't need to see that. That is for the model's purposes. But the instructions that we give to the model are how we steer it. And the idea that the model is pre-trained and post-trained, the black box model, to take some given set of instructions and then proceed is important. Again, the think tokens are often, as we find in the latest models, hidden in blocks that delineate that piece of the context as the the property of the model to generate the tokens it needs to generate the answer. But again, those are distinct from the instructions we give.
So Rao, I have a question here then. Are we doing post-training wrong? So you are saying that the current things that are not really doing the best of all, right?
So yeah, I think research is such that we are always doing something wrong that we will improve a few years from now. And people in academia that you used to be at one point of time, and Joey and I are still, our idea is to try and see what is still missing here. I actually missed one slide. I didn't want anybody to think that this is supposed to be anything negative about LLMs. Skepticism is a good inductive bias for good science. And you just need to understand that the current RL system that basically DeepSeek R1, one of the other things you have to understand is right now we only know one frontier model, how it does actually RL. That's DeepSeek R1. Nobody else writes papers anymore, which is basically you're trying to read the blogs and try to see what they might be doing. And interestingly, the one DeepSeek R1, I have humongous respect for them because they actually publish something. But the point is that actually shows also that the way they're doing it is they make the baseline trajectories be, generate K trajectories and hope that one of them is right. And if none of them is right, there's nothing going on with RL. And that started basically an entire cottage industry of people trying to generate more trajectories, kind of sorting them in terms of the length and taking the few top ones. But if you remember what I said, the correct ones tend to have shorter trajectories, the long ones tends to be wrong. And so when you sorted it, you are essentially picking more and more correct ones. And then sampling just the top doesn't mean is that you spent a lot more time trying to solve synthetic data problem. I've heard 4 times removed that systems, some places like Gemini, etc., are actually doing more more like LLM modulo sort of thing, where they basically might be doing MCT style post-training in the training phase. So all I'm saying is, if the stuff that you write, I can critique and then point out what is wrong with it, and then that actually makes you think about what else needs to be done. So as to are we doing post-training wrong, we started doing post-training right now, and we should understand what is right and wrong about it. And I enjoyed Joey's talk. It's like there are 2 very different things you have to do. One is, given where you are, how do you go forward? And then also make sure that did you get this to the right place, or should you be getting to a different place? And in some sense, that's the complementarity of these 2 things. And we will have better post-trained techniques. We will have less of a craze about intermediate tokens having semantics, because that's just wrong. And in fact, by the way, that actually OpenAI and Gemini most of the time don't show you the think tokens. They show something, and people think that is a think token. That's actually potentially post-facto computed explanation of the solution. So if you see the open source models that OpenAI is sent out, it has 3 pieces. One is think tokens, one is the summary tokens, and one is the solution tokens. And these summary tokens essentially is a part of the solution in some sense, and you're trying to communicate with humans with that. So if you want to communicate, plan for that. If on the other hand you want to think, your thinking doesn't have to make sense to me. Essentially, your thinking only has to make sense to you in coming up with the correct answer.
Joey, you have done a lot of post-training. So what's your insight here?
Yeah, so I was going to say post-training is hard. One thing I think people don't appreciate is the base ingredients matter a lot. If you're doing something like reinforcement learning, it's pretty critical to have some of the basic behaviors present in the model. It is possible, this learning from zero thing, but that just takes a lot of rollouts, in some sense luck, to get to good observations. Things like GRPO really need to have a mixed batch of success and failure to get meaningful signal. Even SFT, which is generally more reliable, it has some risks as we've applied it to kind of mode collapse or loss of other behaviors in the model. I think we don't yet really understand the scope of what can be done with post-training, how we preserve steerability in our foundation models so we can do interesting post-training. There's a lot of opportunity for research there. But what I guess is fun is there's also a lot of opportunity for engineering and trying stuff. And you're seeing a lot of groups around the world trying stuff and writing blogs and tweets and hopefully occasionally a paper, about what they learned in that process.
So you guys talk about reasoning, and some of the questions that I see from the audience is, what is reasoning? So is it reasoning a kind of something that we can solve by pattern match, or is it something beyond the pattern match?
So we call it reasoning. I think your talk was good. In some sense, that's not the right word. It's generating spurious tokens that the model can use to get to an answer. And that these additional tokens allow us to move in the space of this conditional, so that the final set of tokens are the right set of tokens. We as humans attribute that to reasoning. And in some sense, in the demonstrations we've given the model, we've tried to bootstrap that with what is human reasoning. But there isn't a constraint, certainly as we move in the reinforcement learning direction, that this coincide with the standard processes of human reasoning, at least unless we reward it to do so.
Wow.
So I think first of all, you obviously know the answer, Joohung, that there are ways in which we have formalized reasoning. For example, logical reasoning has been formalized, and certain kinds of logical reasoning can actually be connected to pattern matching. It's not one or the other. So for example, databases are doing reasoning, but they're doing direct pattern matching. Detective databases go one level further. Knowledge entailment winds up having logical reasoning thing. The other issue is, if I give you the correct answer to what you considered a problem that requires reasoning, that doesn't necessarily mean that I did reasoning the way you expected me to do it. I give this example of this Microsoft interview question where they used to ask people, why are manhole covers round? If you never heard this, the first time you heard this, you would have to think and actually come up with a good answer. But right now, all you know is people have prepared for the interviews because every damn interview question bank has this. And LLMs have basically not only seen every percentage question bank, during post-training, they're also seeing longer instances of how to solve different kinds of problems. And so in some sense, we are converting reasoning into a memory effect. And that is where we are right now. Nobody has shown otherwise. It's not simple pattern matching, but it's in the spectrum of pure retrieval and something like logical reasoning, we are still somewhere closer towards the retrieval side. But you're increasing the amount of data over which you get to do this retrieval.
So agentic AI requires planning, and the planning has unbounded length, as you say. Right? And you're saying that there is actually no guarantee of success. Isn't that a worrisome issue?
Yeah, it keeps me up. It keeps me up.
What should they do?
It depends. It depends on the kind of world. If your world is ergodic and many things where, until the credit card transactions get connected, calling the right source and doing the right tool calls, etc. It's still very painful amount of activity we do that LLMs are actually good at helping improve. So if you are sort of kind of in the loop, this is still very useful. If the overall thing is basically, by the way, I've seen agentic benchmarks, not the one that Joey may have done, but I've seen agentic benchmarks. Like for example, TrueBench, we are looking to see whether they have examples with action interactions. No, they don't. They make sure that there are no action interactions. So if you actually make your domain ergodic, then it becomes easier. And by the way, when you have a small kid in your home, you make your living room ergodic. You make sure that there are no guns lying around, there are no sharp objects lying around, so that even if the kid doesn't know how to do planning, they won't get into major problems. And that is basically where we are. There's a large number of domains where failure is either soft or doesn't actually exist, so you can blunder your way from one place to another place. And that's where, if you're trying to improve do various operations on some text so that it has a different format, etc. It's not going to hopefully end the world. Whereas if on the other hand, these are actions that actually have physical consequences, or even in the case of databases, you overwrite particular files, etc. Those would make it essentially non-ergodic domains, and you need to make sure that the correctness is true.
We looked at this a little bit in the context of safety. It's a very good point. In the system world, we can often wrap things in transactions to create kind of the illusion of ergodicity. And one of the nice things about doing that is it allows the model to explore to some terminal state and then realize, I regret having deleted the file system. I'd like to roll that back. And so there is some value in preserving ergodicity in our environment so that we can have models that make that assumption and can explore more effectively. But it's a good point. Models generally aren't good about reasoning about the long-term consequence of their actions.
And if you have, like in some sense with the transactions, my sense, if I get it correctly, in some sense, if you have simulators, then a world which is non-ergodic, but in a simulator, it is ergodic because simulators can be restarted. We try to learn in flight simulators because we don't want to kill flights. But then eventually you do have to learn, try to fly the real flights, and that's when things become important. So but then writing the simulator is actually a very interesting, costly affair where flight simulators have to have the understanding of the physics of the world, etc., to make sure that they're giving as good an information as possible to the agent as to what it can get out of this. Normally, this whole controversy about whether LLMs are learning world models or not, even though they are getting predictive accuracy correct, is connected to this. So they can tell you exactly very good paths in Manhattan, but the Manhattan map they learned actually is completely wrong. They can give very good predictions about solar planetary system interactions, but the actual model they learned is wrong. And so they can't use that model as a simulator. That's basically, again, connected to, if you do have a simulator, then an ergodic, non-ergodic world with a simulator is an ergodic world. to some extent.
Okay, so that's a handful of discussions, and I wish we could have more time, but our time is running up now. Okay, so let's thank both Joey and Rao for the insightful discussions. Okay, so thank you.
Thank you.
Okay, so now we are going to move on to our third keynote speaker, Professor Pascal Hitzler from Kansas State University.
Thank you very much. Nice to be here. If you're a little bit like me, then after an hour of dense and interesting talks, your brain may also be a little bit tired. So I'll try to keep this focused on a single point mostly, or a kind of type of problems that has eluded researchers for 20 plus years. And only very recently, with the advent of large language models, there finally seems to be a way through. And that is rather exciting because it is a problem of rather significant import, as we will see as we go along. And that brings us right to knowledge graphs. Now, what are knowledge graphs? Knowledge graphs are, generally speaking, a prominent paradigm for data integration and management, but that's kind of not our main point here. Think of knowledge graphs as a type of specific database expressed as a labeled directed graph, if that you came across that term, structured in a specific way, that contains information about entities and their relations, and it can possibly be rather large. And knowledge graphs as such have been developed, have been around in order to make it easier to deal with large-scale data, multi-source large-scale data, bringing it together for multiple use cases, etc. And that's actually an area of research and technology that predates large language models, agentic AI, all the things we're talking about right now. However, if you have already heard about knowledge graphs, then it is more likely than not that you may have heard about them as something that is in the vicinity of agentic AI and large language models, particularly because there is some work that shows that they're particularly useful to help large language models in areas where they're sometimes not so good. We heard about some of these things earlier. They may just sometimes give us nonsense, for example. So having a high quality database, knowledge base, if you like, and have it interact with the large language model in some way to help improve the quality of outcome, that's something that has been done, that is being done, and you may have heard about the term graph rag, for example, which is one of the prominent approaches right now for this. But that's actually not what I want to talk about. I want to kind of go one step back here. And if we're at the stage where we see that knowledge graphs, having these highly structured databases, are helpful for this type of agentic AI, where do these knowledge graphs come from in the first place? And that brings us back to this old wicked problem, in a sense. And I'll talk about that in a second. In the context of all this, I wanted to mention that not too long ago, Samsung actually acquired a startup out of the knowledge graphs community from a very prominent research group, Oxford Semantic Technologies, a knowledge graph startup. So just wanted to say there are these connections already at hand. All right. So what are knowledge graphs? Let me get to this, and then let me get to the wicked problem. And just look at the box which you see on the right-hand side. The second row here, the second little graphics here. Knowledge graphs consists of entities and their relationships. So for example, there could be an entity in the knowledge graph, call that a node, like Kansas City, for example. And there would be another entity like the number 516,032. And those two entities could have a relationship like these 500,000 would be the population of Kansas City, for example. Part of this knowledge graph would also be a type structure, a schema for this. Like, for example, something of type city that's above that would have a population expressed with something of the type positive integer, for example. In knowledge graphs, you usually think of this schema information could call this an ontology of sorts, together with the actual data graph underneath it. And now in a knowledge graph, you would have a lot of these entities densely interconnected with each other. And that actually constitutes a knowledge graph. Now, that sounds rather straightforward. It actually isn't. And let me just explain to be why it often isn't. The example I just gave you seems very intuitive, but you could start asking, what Kansas City do you actually mean here? Like, if you ask anybody in Kansas, I happen to be in Kansas, what is the population of Kansas City? More often than not, people we say, probably about 2 million. So where does this come from? Why does it say 500,000 here? And I say 2 million, or is this just a mistake I made? So what actually do I mean with Kansas City? That's the core of this question, because Kansas City can be a lot of things. Most of what I consider to be Kansas City isn't even in Kansas. There is a Kansas City proper, which is in Missouri. There is a Kansas City metro area, which has the 2 million inhabitants, for example. Now, there's another question is, well, 516,032, was that this year or last year, or 10 years ago, or 30? Perhaps it was Kansas City Metro 30 years ago. Who knows, without further information. All this information seems to be missing in our little snippet. Shouldn't we have things in our knowledge graph which kind of say all these things, more connections, more types, which explain this? To what level of detail would we need to go? Another statement would be, well, if what does this mean in the schema level? A city has a population which is a positive integer. Formally, you could express this in a line such as the one beneath, which would say has population, has as domain city, meaning the kind of left-hand side of the arrow is always a city, and then the next thing, range, would be a positive integer. Right-hand side is always a positive integer. But then you have the problem that other things have populations as well. For example, states. So kind of, is this now a problem or not? What do we actually mean with this statement? Well, there are standard languages for this, which have been around for 20 plus years, which tell you what exactly you could use and what not. But it probably explains already that you need a little bit more careful if you kind of want to be more exact in what you actually want to express. So for this reason, in particular on the types like city or positive integer, ontologies, schemas, allow to express formal relations using formal logic, like, for example, the one expressed in the next line saying, in English, every city has a population that is a positive integer, which seems to be a statement that makes sense. But we can ask more questions, like, for example, how did you come up with this number? Nobody actually counts people in cities. Every number you get as a population number is a number somebody arrived at using a statistical approach to estimating the number. So somebody who may be interested in looking at this in more detail rather than a kind of just a glance at numbers saying, what's the ballpark of population of Kansas City? But somebody who may be a demographer, for example, may want to know, so what actually was the statistical method used here? What is the base data that was used? Where is that? Shouldn't that all be listed in the knowledge graph as well? Well, for that person, perhaps. So you see that knowledge graph isn't equal to knowledge graph. So knowledge graphs are more self-explanatory. They keep more information. Some are more granular, some are more coarse. There's different reasons for having different knowledge graphs. And making a knowledge graph, in particular at a kind of high quality level that is rather granular, needs expert knowledge. Like, for example, if I would like to also list the statistical information, statistical method, how they were used, inputs, outputs to that, etc., algorithms, then the graph is going to get complicated. And I probably need a statistician to explain to me what all that means. And perhaps not only a statistician, but probably also some other people who understand about populations and how these are assessed in the real world and how surveys are done and all these kind of things. So, and that brings us to the wicked problems. While these knowledge graphs are really helpful, and this has been shown before LLMs came along, they're helpful for large-scale data integration, for getting the data together and then do something with the data, answer questions, complex questions if necessary. Then making these knowledge graphs and the corresponding schemas is very expensive. It's primarily very expensive because it needs expert time. It needs experts from all the relevant areas to come together, discuss with each other what is a good schema, discuss with each other what is a good structure for the knowledge graph, and then realize the knowledge graph. The technical realization of the graph afterwards is actually much easier, but designing the thing in the first place is a lot of work. So, and of course, now we have a research area. Actually, the semantic web research area is where this all comes from originally, which is 25 years old. And of course, computer science researchers have looked at automating or semi-automating creation of knowledge graphs, other engineering tasks around knowledge graphs, like, for example, integrating knowledge graphs, taking two or more knowledge graphs, putting them together into one big one because you need the data together. And how can we actually save time and effort doing that? And it turns out that that is hard. That is really, really hard. And before the advent of large language models, it was kind of not really clear when we will ever make a dent into that big problem. All right. And now enter LLMs. And now I'm not bringing this back to LLMs because I want to talk about how knowledge graphs can help LLMs. We have a lot of research around GraphRag and other methods which show that, yeah, there is significant promise. And of course, the research has to stabilize. I'm looking at the other problem. Where do we get the knowledge graphs from? And can we actually use LLMs to make these knowledge graphs, which we can then use for whatever purpose we want to? And, well, at the first glance, it seems clear. LLMs really can act as a type of natural language-based database, which you can query. You ask it, you get information back. The information is more often than not reasonable. And then also we know that it is possible to receive structured outputs from these large language models. Like, for example, in coding assistance. Coding assistance seems to be a thing that everybody accepts now as, yeah, this is helpful just because they experience like that. I actually do not know if there's any formal studies looking into that, but it seems clearly helpful. So likewise, one could look into this natural language-based databases that large language models are and say, give us structured output in the form of knowledge graphs, for example. Or I give you two knowledge graphs, use your common sense natural language-based database to integrate these two knowledge graphs into a bigger knowledge graph. And it seems that that should be possible. It should be possible to help humans do that, such that not as much time and effort of humans will be required to do that. Well, in this big theme, there's different sub-problems which turn out to be hard. One I mentioned already is making a good schema, ontology or schema modeling. Actually constructing a knowledge graph based on a schema that has already been developed. Some people call this ontology population. And another one would be, as already mentioned, the integration of knowledge graphs via ontology integration or alignment, a mapping between ontologies. And I'll particularly talk about the last part because I think it's the clearest case where large language models can help in the context of what has been done so far. All right, so let's see what some issues may be that crop up in this context. And the issues really are issues that, well, some of the issues, at least, that we know large language models have if you want to apply them to something where quality is actually important as an output. Hallucinations are one of them, or general output quality. As Subbarao also mentions, they often give you good stuff, but sometimes they just give you nonsense. Scale may be a problem, prompt size. If you talk about knowledge graphs, we released, I believe, probably the world's biggest geo-knowledge graph a few years ago with, I believe now about 20 billion node-edge node pieces, triples as they call them. So that's big, right? You can't easily just feed that into a prompt. So you need to deal with that. And then, of course, knowledge graphs may also be about niche themes because you may want to answer some very specific questions, even more specific than what are methods to assess populations of cities, for example. So some may be addressable, of course, and I'll come to that on one of the later slides. But how exactly actually can we get towards addressing them? And what are key bottlenecks we can look at here? All right, so the example which I want to talk you through, which is one of the problems in the context of ontology engineering that has been evading researchers quite a bit, is in the context of ontology alignment. This is about the following scenario. You have two knowledge graphs with two ontologies, and you would like to map the data from one graph to the schema of the other graph in such a way that the two graphs become integrated. Now, there's a lot of things involved in this, but one of the things that you want to do for that is essentially map the schema to the schema. And there's an example at the very bottom here. This is a rule, a double implication rule. Think of the first line of the rule in the bottom three lines. The first line here as an expression coming from the first ontology. It talks about awards. This would be funding awards, project, for example, research project awards. X would be such an award, and it would have a co-principal investigator, say, which would be given here by a variable Z. Now, the other two lines are an expression, again, a logical expression, which pertain to the second ontology. X again here, but it would be called a funding award in this ontology. It could also be called completely different, but let's assume it's called funding award. This funding award provides an agent role Y. This agent role is a co-principal investigator role Y, which is performed by Z, again, our co-principal investigator. If this seems weird to you, kind of why is there this chain of things? That's actually a very common technique in knowledge graph modeling, because that gives you the opportunity to attach a lot of contextual information to the pieces, which may help you understand, for example, that Kansas City is the metro area or something else, for example. So ontology alignment is about feeding these two schemas, these two ontologies, to a system, hopefully an LLM in our case, and asking it to actually come up with this rule, which gives us the mapping. Now, this is a rule which actually comes out of a benchmark, which is already a few years old, precedes the LLMs, and this is an example for a complex mapping. Simple mappings are just about finding types like award and funding award and saying they should be equal. But of course, the more complicated, the more important problem is to actually find all these mappings. Now, before recently, essentially finding complex alignments was virtually impossible with automatic means unless you have really strong assumptions, like, for example, a shared knowledge graph with two schemas, which are just not really realistic for realistic scenarios. So essentially, we didn't really know how to do it. For the simple ones, which just look at types and mapping into each other, the situation was much better. Don't need to talk too much in details here. Mostly string similarity metrics actually did a lot of the job, and now LLMs can actually do similarly well on these simple alignment problems. And that's fine and that's good, but we want to look at the complex ones. The example I was giving you is actually out of a benchmark called the GeoLink benchmark. This is out of a real integration effort of two ocean science databases, large US ocean science databases. And so we had then at some stage these two ontologies, and we mapped these two onto each other without even thinking about making a benchmark. And only later on we said, well, okay, we can just release it. Now, if you take this benchmark with these, I believe, 109 rules or so, which we had there, so it wasn't terribly big, just 109 rules. Also, the ontologies are not terribly big. We're probably talking about dozens of classes. And you just feed them to a large language model and say, give me the rules, then essentially it doesn't work. We even gave it a slightly simplified scenario. We didn't ask for the rules. We just said, well, if we give you, say, the left-hand side of this rule, just the kind of the top line here of this rule, and say, this is from the first ontology, then give me only the predicate names from the second ontology that we need to assemble the rule. That's a simple problem, right? We don't ask for the rule just for the pieces which need to be assembled, but that would still help a ton because you give that to a human and the assembly is really easy. So we asked the simpler problem to LLMs, and it turns out that they kind of gave us about 4.5% correct of what they told us. That is clearly not enough, even for semi-automation. That's just not helpful. 5% is just not helpful. So what can we do? Well, and in comes a second idea, and that's the idea of ontology modules. I don't want to go into detail, just focus on the red here. Ontology modules are essentially a method to divide and conquer. You think of an ontology, the schema in that case, and then by proxy also the knowledge graph itself, as a set of parts which are interconnected parts of the graph or the ontology, which kind of make sense for a human. And let me just give you a little graphics here first. This is essentially a depiction of a schema. There's no logic here. Underlying there is actually logic. This is just a simple depiction of types and how they can be related to each other. And this is actually an example from a supply chain tracing ontology in the knowledge graph, which we actually did with application partners. And for example, down here on the left, there's events, which are events important to the tracing in a supply chain. Like, for example, every time you have a data point, like, for example, the container actually changed hands or changed owner or was sold, things like this. And at each of these events, you get a record. So if you have a string of these records assembled in a trajectory, the trajectory is up on the upper left, while the event is on the lower left. Then you can actually put these points together in a trajectory. In the middle, there would be a piece which gives you the container into which the goods are actually packaged, for example. And there's more of these pieces on the right. And well, these gray boxes, which I just pointed out, trajectory, container, or event, these would be modules. So each module of this big schema talks about something that makes sense for a human expert. It makes sense to talk about supply chain events. It makes sense to talk about trajectories, about containers in this context. And so the whole ontology, and therefore the knowledge graphs, falls into these different pieces. Now you would say, well, that's kind of trivial. That makes sense. Perhaps you do. Well, the reality is that for 20 plus years, ontologies have been modeled without doing this. You just get the big thing, the big interconnected graph without any internal structure. Although, of course, the people who would initially model this ontology, they would usually have this internal structure in their heads. It would just not end up on the ontology. So the change here is to say, well, let's not get rid of that, but rather when the ontology is made, let's keep this modular structure so that we can make use of it. And making use of this in the context of ontology alignment actually worked like a charm. So a module is a part of an ontology that constitutes a conceptual unit in the eyes of a domain expert, like a trajectory, for example. And yeah, there's tools to deal with them, etc. Now back to our benchmark, the GeoLink benchmark. What you see here in the upper part is a diagram, and this is not a diagram for the ontology now. Each of these nodes here is actually a module, and what is shown here is primary relationships between these modules. So we have about, 20 modules or so, or 18 in this ontology. And 18 is much better than several dozen. So what we did now is we used exactly the same problem, namely the find us these pieces for the alignment mapping, for which one example we saw earlier, but we now made that a double stage process. The first one was we gave it again part of the map of the rule from one ontology, and then gave it a list of the modules of the other ontology and asked the system, which module or modules do you think you will need to find the pieces for the mapping? And the LLM told us, well, for this one, we need the agent role, for example. And then in the second stage, we fed the LLM only the modules it requested together with the original question, and it came back with its answer, namely the pieces that the LLM was claiming we would need to make the rule. And it turns out that we went up from 5% correct to 95% correct. And that was quite breathtaking. I mean, we expected that it would work better, right, than not having the module. But honestly, I did not expect that we worked like a charm. In the meantime, we replicated this experiment on a second benchmark. That's the only two benchmarks we have which have modular information at the moment. The other benchmark is completely different. It's about the history of the slave trade, also very, very differently structured, and the results are essentially the same. So that was quite breathtaking for me. All right, so I think I have 4 minutes. So there's additional evidence that modules are helpful for LLM-assisted knowledge graph and ontology engineering. I just talked about ontology alignment because I just kind of, for me, was the most striking example. We also looked at ontology modeling. We looked at ontology population. We also have initial indications that modules are really helpful there as well. They essentially help you to chop down the problem, to do the divide and conquer. All right. I promise to come back to some of the obstacles which you often have when doing something with LLMs and how they could be overcome. Human in the loop is one of the things that can help with hallucinations, for example. Of course, 95% is not solving the full problem, but 95% will go a long way of making this very expensive task much easier and therefore much more cost efficient by just kind of solving 95% of the problem, throwing the rest at the human, probably with some nice interfaces to do that, which of course need to be developed. General output quality, again, that can be addressed by using good ontology modules or something very related to that, which is design pattern libraries. For example, when we want to make good ontologies, don't start from scratch, use modules from other ontologies, which are known to be good to make your new ontology, for example. Scale, the divide and conquer approach using modularization, as I just talked about, I think can be a key ingredient to this. And dealing with niche themes, like you need a knowledge graph on a very specific niche theme, combinations of fine-tuning, human in the loop, specialized ontology design patterns and modules may be a way to address this. We do not know at this time. This is all ongoing work, of course. So, conclusions. LLMs bear a significant promise to accelerate knowledge graph and ontology engineering by assisting human experts. I think this is clear now, and that was kind of the hope the community was following since LLMs came along, and I think we have clear indications now. Of course, the details need to be worked out, and it's a very good time right now to look at that, because there's breakthroughs to be had here, and you want to be ahead of the curve, of course. Exact methods need to be established. And there's also seem to be clear indications that divide and conquer methods, ontology modules in particular, may play an important role in obtaining useful LLM outputs in some cases. So, going back to the very beginning, I was talking about knowledge graph engineering using LLMs to accelerate and essentially also make cheaper knowledge graph engineering, meaning the creation of knowledge graphs and the integration of knowledge graphs. Knowledge graphs at the same time are currently being looked at as major ingredients in agentic AI, using knowledge graphs to, for example, bring more grounded truth to LLM computations to make sure you get more quality output. There's significant indications that that is exactly happening. So closing the loop here in a sense. Thank you very much. I'm at the end of my time and I'm happy to take any questions.
Thank you. So let me mention that this is a long line of research on knowledge graph, and LLMs start to play some roles in this line of research, right? So what is actually the main users of this ontology alignment? So is it for human readable and manageable by humans, or is it to be feedable to machines to automate?
So the answer is both. It depends on the use case. So the ontologies and knowledge graphs as a proxy, they have the particular strength that they can straddle between the human conceptualization of information and kind of the way we structure data. If you look at traditional databases, then often kind of they're not necessarily done with much heeding towards kind of how does human experts think about kind of what data should go together and how it's named and how it makes sense and so on. Ontologies are made in such a way that on the one hand they allow data access to raw data, to the data that was produced, whatever, by census streams, by user interaction, by capturing whatever information that may be important for personalization, as we had seen an earlier speaker talking about. And at the same time, it helps to organize the information in a way which makes sense for humans, how a human expert conceptualizes it. What's the advantage of doing that? The advantage of doing that is that everything you want to do with this integrated data is easier if the data and the structure of the data is easier to understand for the human. Like, for example, you want to have another data set and you want to add this new data set to the data set you already have, and the software engineers who worked on this a few years ago are already gone, right? So the closer the data is actually to the understanding of the human experts, the easier it is to retrace what is actually in there. How do we understand this? How does this make sense or not sense? What is good, what is bad? The easier it is to work with this data, put more data in, modify the data, restructure it, reuse it for a new purpose. So essentially, rather than kind of old school approach, you have one specific problem, you get your data together, you integrate it once, solve your problem, and then you have your problem solved. But then if you have a related problem, you need to start from scratch and integrate your data again. Knowledge graphs give you the advantage that you do it once in a more principled way, and then using it for an adjacent purpose becomes much easier. And that's essentially the main value you can get out of it.
Okay, so when the knowledge graph is in the form of triple, right? And for some reason, this triple form helps the researchers to find out the expressivity and the computational issues, right? On the other hand, when this is being used by LLMs or AI, it doesn't really matter what forms that this will take. So you can just store the triples and make a sentence and put it into the prompt of LLM, and LLM can do something based on that, right? So do you think the form of knowledge graph that we have, is it suitable for to be processed by LLMs? Or can there be a better representation, or can there be something else?
So let me retrace on your first part, on the first part you said, and just emphasize that it's not just one triple that we feed, right? So the advantage of a knowledge graph is that you have all these relationships to a node, a lot of triples and triples of triples, and chains, in a sense, like thought chains, you could say. And you have all these things connected to each other. So you don't feed one triple, you feed a piece of the knowledge graph, which, for example, if you think of modules, would be all the things that are related to a certain concept in the mind of an expert in the topic in which you're currently looking at. And that's the advantage what the knowledge graphs can get to you. Now, to your question, kind of, are we doing the knowledge graphs in the right way to get the best advantage here? And the answer is, well, nobody knows at this point for LLMs. Even for humans, human users, traditional users of knowledge graphs, for data integration management, whatever, information search systems, or over integrated data, it depends a lot on your specific use case, how you best structure your graph, how you get at that. So it depends on what you need, how complicated you need it. And I believe that the same will actually be the case for large language models. So one way to get at that is to make a graph that is very fine granular, contains a lot of information, but then in some cases you may actually only take a much coarser look of that. Like, for example, if you do not need to know about the statistical method coming up with the population of Kansas City, you just feed the population because that may just do what you need currently, and that's fine. And it doesn't matter if the original graph also has this additional information, because you could just throw it away before you feed it actually to the model. There's a lot of research going on in that context, of course, as well. We still need to understand what are the best models, knowledge models for this, and whether the best one in the end, or the next one that will really help, will be a graph model. Nobody knows. It's currently the best we have.
Okay, so thank you very much.
Thank you.
So after a 3-minute break, we'll resume the second half of the sessions. Welcome back. Our next speaker is Professor Stefano Ermon from Stanford University.
All right. Thank you so much for inviting me to this event. Very excited to be here. And for those who don't know me, my name is Stefano. I've been a professor of computer science at Stanford for about 10 years, leading a research group focusing mostly on generative models, what's now known as generative AI. And my group is mostly probably known for the early work that we did on diffusion models. We kind of like developed some of the very early models back in 2019, where the field of image generation was kind of like dominated by generative adversarial networks. We came up with this alternative approach, what's now known as a diffusion model, that was achieving much better results. And since then, I've been trying to get diffusion models to work on not just on image generation, video generation, but also on language and code generation. So getting diffusion models to be able to generate a more discrete kind of objects. And that's kind of like the topic of the discussion today. I wanted to share some of the research I've been involved in trying to get diffusion models to be competitive with autoregressive models, not just for image, video, continuous modalities, but also for discrete objects. So to give you a bit of background, you probably all are very familiar with all the excitement that there is today around generative AI solutions. Again, I've been working in this space for a long time, probably almost a decade. I still remember back in 2014, where we were working on building little generative models that could create images for MNIST and very low resolution, kind of like black and white images, very, very poor kind of results. And it was even hard to write papers about this topic. You had to, the papers were getting rejected because people would not kind of understand why would you ever want to build a generative model. It kind of like didn't make sense, and we had to motivate the research and the papers by telling these stories about how one day using generative models we'll be able to learn features in an unsupervised way from unlabeled data, and that will help us do supervised learning, which was what people cared about back in the day. But obviously, since then, the field has made an enormous amount of progress. Like, it's almost unbelievable the kind of results we are able to achieve with existing generative AI models. We have models that can create beautiful images, just starting from captions. We have models that can convert sketches, the kind of sketches I could create, like the one you see there on the left, into, again, beautiful images, kind of like enabling people to express themselves as artists. Obviously, video generation is extremely exciting. We have systems that can create videos on demand just based on prompts, like you see there from a model that was, I think that's from Sora from OpenAI, one of the state-of-the-art models. And then, of course, lots of excitement around chatbots, text and code generation. We've heard in many of the previous talks were focused around LLMs and the capabilities that are enabled by these systems that can create text, that can write code for us, agents. Lots of excitement around the progress that we've seen in language and text and code generation. Now, when you think about the state of the space, it's kind of interesting because there's kind of like two main types of generative models that exist today. When you think about continuous modalities like images, video, even music, all the best models, the state-of-the-art models that are out there are based on diffusion. This is the kind of approach that I mentioned today, something very close to my heart, where you're kind of like generating the content by some kind of iterative refinement process, where you start from noise and then you gradually refine it until you get the final image or the final video. On the other hand, if you think about text and code generation, for example, LLMs, ChatGPT, Gemini, Claude, they're all based on an autoregressive approaches, where you're kind of like generating left to right, one token at a time. And so as a researcher, this is pretty exciting, right? Because it kind of like begs the question, what's the best model? Like, why aren't we using auto-regressive models for image generation? Or why aren't we using diffusion models for text generation? What's the best approach? Like, is there a better kind of like statistical model that we can use to eventually build the best generative AI solution, right? Kind of like probably a lot of people would agree that generative models seem like a pretty reasonable path towards human level intelligence. Perhaps you buy into the Richard Feynman quote about, what I cannot create, I do not understand. Is sort of like this idea that in order to be able to really understand the meaning of a concept, what it means, what's an apple, or what it means to understand Korean, for example, you need to be able to generate. You need to be able to draw an apple. You need to be able to speak Korean. And so it's pretty clear that generative AI is a super important technology, but at the core of generative AI, we're just building statistical models. And so as a researcher, it's pretty exciting that there is this dichotomy where there's two types of generative models that we use today, and one is good for continuous data, one is good for discrete data. What's the optimal approach for building a generative model? And so again, kind of like if you think about at the highest possible level, there is autoregressive models, which at a very high level, they work by generating content one element at a time. So if you think about image generation, they might generate an image pixel by pixel, left to right, like you see there. Or if you think about text, they might generate text one word at a time, one token at a time. And on the other hand, if you think about continuous modalities, you have diffusion models that they work like this beautiful image of an astronaut riding a horse that you see there on the top right, where the image is generated all at once by refining the object. You start with pure noise, and then you gradually see the image appearing. Very different kind of generative process. And it's interesting that one approach is better, state of the art for images, video, music. The other approach, autoregressive models, is currently the most widely used for text and code generation. And I've been doing a lot of research, basically dating back from the very first diffusion models that we were able to build on image generation, trying to see, is there a way to get diffusion models to work also for text and code generation? And that's going to be the main topic of this talk. I'll try to convince you that perhaps there is a change coming, and diffusion models, when they're built in the right way, when they're trained in the right way, they can be competitive with autoregressive models. And I can see a future where all future large language models are no longer going to be based on autoregressive modeling, where you generate slowly one token at a time, but instead they're going to be generating answers, answering questions to us, writing code for us, using a diffusion approach, kind of like you see there at the bottom right, where you kind of like start with the whole answer and then you iteratively refine it until you get the right solution. So to dive a little bit right in, pretty much all or most of the existing large language models are based on the autoregressive paradigm. And it's a very simple kind of like approach where you're essentially reducing generative modeling to something we understand, supervised, which is basically just discriminative modeling, supervised learning. So all you have to do if you want to be able to generate, let's say, text, is to train a neural network that can predict what is the next word going to be. And if you can do a pretty good job training this kind of model, you can train a neural network to predict the next word reasonably accurately. And again, this is, at the end of the day, a standard classification kind of problem. Then what you can do is you can generate answers to questions, or you can write code. You can do a lot of interesting things just by basically sequentially predicting words in a left to right way, one word at a time. And so let's say you start with a prefix like once upon, and then you get the trained LLM, this classification model, to predict what is the next word, and maybe we'll predict A. And then what you do is you just take this prediction, you feed it into your context, and you get the neural network to predict what is the next word after once upon A, and then maybe we'll predict time. Then you get this new word, you feed it again into the context, and you predict the next one, And so you get once upon a time there, and you keep going. And that is, at the end of the day, the whole idea behind existing large language models, max token prediction, and you just sequentially unroll them at the inference time to get answers to your questions. That's very, very simple. It's probably the simplest kind of generative model you can think of. It's nice because it's just reducing generative modeling to classification, which is something we understand. It's something we had a lot of success using deep learning. It's just training large neural networks to do increasingly well on various kinds of prediction tasks. In theory, it's actually a very flexible kind of like formulation, although it might seem like it's pretty restrictive to generate based on this approach, one word at a time. In theory, just because of the chain rule of probability, any joint probability distribution can be factorized into a product of conditionals. And so to the extent that you have very, very flexible, very, very powerful neural networks, this approach can, in theory, represent any kind of probability distributions, including very complex ones. And it's also like, if you think about the way you ChatGPT generate answers to your questions, it's a pretty reasonable kind of like inductive bias. If you think about how we write text, we tend to write, again, kind of like left to right. Perhaps, there is a little bit of iteration. If you're writing a paper, if you're writing a document, maybe you start with bullets and then you refine them. But the idea of generating left to right, it's kind of reasonable. And perhaps that's one of the reasons these models actually work so well for text generation, code generation, all the kind of exciting applications that we've seen also in previous talks. Now, if you think about the downsides, it's also a pretty simple kind of like approach where a lot of things could go wrong. Perhaps the most famous one is this idea of sampling drifts or compounding errors. Jan LeCun is known to be a critic of this autoregressive paradigm. He's said publicly multiple times that he doesn't believe that this will get us to human-level intelligence and that this approach is fundamentally flawed. And the basic idea, the basic problem, very intuitively, is that you're feeding your own predictions into the model. And so, realistically, your model is never going to be perfect. It's going to make mistakes. And then you're going to feed these wrong predictions into your context. And the data that the model is seeing starts to look more and more different compared to the ones it's been trained on, because there are these mistakes that have been introduced by the LLM itself. So eventually these errors compound, and eventually you're going to get the wrong answer. And that's kind of like a very sort of like old type argument that people have been using for a long time, even in the context of dating back to the 90s, where people were building the first prototypes of self-driving cars. This kind of approach, which in that context is known as behavioral cloning, is known to have these sort of issues, and that it's very hard to get it to work in many other contexts other than language, where we've seen that the results are actually reasonably good. It's also not a particularly reasonable inductive bias, this left to right generation for non-language tasks. Like if you think about generating images, there's no natural order. You wouldn't generate an image pixel by pixel. The way you draw an image is quite different. And similarly, if you think about DNA, other kinds of modalities, they don't have this kind of like left to right inductive bias. It's also kind of like forcing you to use a pretty constrained kind of architecture where you're only allowed to use the context to the left to generate what comes after you, which is potentially pretty restrictive, because we would like our models to be able to use all the information and be able to use information to the left and to the right as they make edits. So in practice, this is forcing you to choose certain kinds of constrained architectures and limit the kind of neural networks you can use to solve the kind of prediction problems that you need in order to generate text. And perhaps the biggest limitation is that it's very, very slow. This kind of, if you think about the way generation works, it's very sequential. You're effectively, it's a for loop, effectively, where you need to generate one word at a time, and you cannot generate the 10th word until you generate everything that comes before it. And so this kind of generative approach, it's extremely sequential, and it does not map well to parallel compute, to GPUs, where we would like to be able to process many different things in parallel. You have a very kind of sequential type of dependency graph that does not enable a lot of parallelism that we would like to use in order to make these LLMs even faster, even cheaper to serve at scale. Now, the alternative approach, the one that is very close to my heart and works best for image, video, and music generation, is based on diffusion. It's a very different kind of generative procedure where in order to define it, the best way to think about it is to think about not the process of generating data, but the process of destroying structure in the data. And so you can imagine a process where we start with, let's say, images, like the one you see here on at the bottom left, and then we slowly destroy the structure in the images by adding noise to the images. And if you keep adding noise and adding noise and adding noise, eventually you have destroyed completely the structure in the data, and you're going to be left with something that is pure noise. And so even in this kind of like little heat map that I have there at the top of the slide, you can see how a multimodal, bimodal distribution P0 is slowly converted into a single, simple Gaussian distribution by adding noise through this diffusion process. I'm not going to go into the math, but the critical thing to think about is that if we somehow were able to flip the time axis and go from noise to data, then we would have solved the generative modeling problem, right? If we somehow can flip the direction of time and we can go from noise to data, then we have built a system that can generate images for us, that can generate videos for us, that can generate music for us. And this is the core idea behind diffusion models. This is how diffusion models work. At a very high level, again, there is still a neural network involved, but the neural network is not trained to predict what is the next token, what is the next pixel. The neural network is trained to remove noise. So you train the network to take a noisy image, let's say for image generation, and try to figure out how should I remove noise, how should I clean it, how should I produce a clean image corresponding to this, let's say, noisy dog. And again, this is something that you can do at scale. You don't need any labels. You can just take very large amounts of unlabeled data. You just add noise to the images and you train the model to remove the noise. Now, how do you use this model at the inference time? Well, the basic idea is that you can start from pure noise, and then you can gradually use this trained model that you have to fix mistakes, remove noise until you have a clean image. So you can start from pure noise, and then you slowly remove noise. You gradually refine the image using this neural network that you've trained until you get your clean sample at the end. And this is the approach that is originally came out from my lab in 2019. Then it was later picked up by a lot of industry players, Midjourney, Stability AI, the Sora models, VO, Imagen. They're all based on this core idea. And this makes sense because diffusion models have a lot of advantages. The network that is trained to remove noise can have any neural net. Basically, there's no constraint on the kind of neural network architecture you can use. You can use context to the left and to the right as you remove noise. There's literally no constraint. You don't need any causality. You don't need any causal attention masks. You can use any neural network you want. You're able to use all of the context to figure out how to solve this denoising task. Training and inference are decoupled. So as you think about sampling from these models, at the end of the day, what you need to do is you need to solve an ordinary differential equation or stochastic differential equation. And so it's possible to use numerical techniques and discretize time in clever ways so that you can generate from these models really, really quickly, like instantaneously sometimes. You can also trade off quality for speed. After you've trained the model, you can decide basically how much compute you're going to use at the inference time to control how much you care about quality versus how much you care about speed. Turns out the models tend to be more data efficient. They tend to be a little bit smaller compared to the kind of like massive autoregressive models that people usually train on text and code. They support controllable generation. I'm not going to go too much into the details, but the idea is that because you're working with the full object to begin with, it's actually a lot easier to steer a diffusion model in a certain direction. So if you care about, you have certain constraints that you need to enforce on the output, or you have some other kind of reward function that you want to use to kind of like bias the generative procedure in a certain way, it's very, very easy to incorporate these constraints in a diffusion model, because you know from the very beginning what does the object look like, and you can kind of like push the denoising process in a direction that will also, let's say, satisfy some kind of constraint that you have over the outputs. And it also has this nice kind of like inductive bias where the model is trying to fix mistakes, and then at the inference time, it's used to correct mistakes, which is quite different from an autoregressive model where once you output something, you can never take it back. A diffusion model is actually trained to fix mistakes, and so it could be potentially more robust to mistakes that are introduced by the fact that it will never have a perfect denoiser, as we will never have a perfect model that can predict the next token. So what are the downsides? Well, it's been hard, very, very hard to get diffusion models to work on discrete data. And the reason is that if you think about diffusion, that's a very continuous kind of process. It involves stochastic differential equations or partial differential equations, the Fokker-Planck equation. Kind of like involves this idea of taking an image and adding noise. There is a lot of geometry that you kind of like need to have in order to build a diffusion model. You need gradients, you need the calculus, stuff that does not necessarily have an equivalence in the discrete world where you're thinking about text. Like, what does it mean to take a word and add noise to it, right? It's less clear. Or what does it mean to interpolate between two words? There is not necessarily an obvious counterpart. So in order to define a diffusion model for let's say, text generation, we can try to follow the same kind of argument. First, we can define a process that we can use to destroy structure in the data. And this is a process that essentially will add noise to the data. And there is several ways to do it. One way would be to just randomly delete words. Instead of adding noise, we can randomly delete words. You keep deleting words, eventually you completely destroy the structure in the data. There's no information left. You cannot make sense of the original sentence if you keep masking out words from that sentence. And another possible process that you could use to, again, kind of like corrupt the sentence is to randomly swap some of the words. So you can start, where are we going? And then maybe you take the first and the third word, and then you swap them. You swap where with computer, and you swap we with moon, and you end up with something computer, are moon going, which makes less sense. And if you keep swapping more and more words, again, you kind of like destroy the structure and you're left with something that has no meaning. Now, once we have this process that can gradually kind of like take data and destroy it by removing all the information, by adding noise in a suitable way, we can train a model to reverse this process, just like what we did in the context of image generation. We can try to train a model to correct these mistakes. Let's say, take a sentence where some of the words have been masked out and predict all the missing words. Or you can take a sentence where some of the words have been flipped, maybe you don't know which ones, and the model has to fix the mistakes, has to correct the sentence by, again, fixing the words that have been flipped. And if you can train such a model, then again, we can use the same idea that we had before, this idea of start with pure noise, and then just get the model to keep fixing mistakes, keep refining the output until you get a clean answer. And so it might look something like this. You start with random words, and then you keep fixing them until you end up with something like, running is great for your health, right? Similar to pure noise data. Or, if you have masks, then you can kind of like start with pure mask, and then you get the model to infill some of the words until eventually you have full sentence that actually makes sense, like running is great for your health. Now, it turns out that this approach actually works really, really well. So if you train the neural network in the right way and you define a suitable continuous time process, which is kind of like a diffusion over a graph, you can use a lot of the ideas that worked well for diffusion models, and you can translate them to text generation. So we had a paper last year where we introduced a method called SAIF, a score entropy discrete diffusion model, which is actually really exciting because for the first time, we were able to match the quality of an autoregressive model at the GPT-2 scale, so at relatively small scales. We were able to train a diffusion language model that was able to match and in some ways surpass the capabilities of an autoregressive models of similar size trained on the same data. Kind of like highlighting that maybe diffusion models could be a better approach if they are scaled up in the right way. And this plot here on the left is perhaps the most exciting kind of result. And what this plot is showing is it's showing the quality of the samples that you get using this diffusion approach, this refinement approach, as a function of the number of denoising steps that you do. Like how many times are you going to call your neural network to remove noise to clean up your sample? And the more denoising steps you do, the higher the quality. So on this graph, you want to be as low as possible. So generative perplexity is a metric of sample quality. So you want to be as low as possible. And as you can see, kind of like at two different sizes, GPT-2 small and medium, you can see that kind of like the quality keeps improving as you increase the number of denoising steps. But what's exciting is that the quality is the stars here. The stars basically correspond to an autoregressive model with the same number of parameters trained on the same data. And in order to generate 1,024 samples with one of these autoregressive models, you need 1,024 neural network evaluations. So you need to sequentially go and generate all the tokens, which can be very, very slow. And what's exciting is that with that diffusion model, we're able to essentially match the quality of what you would get with an autoregressive model run for 1,024 steps using far fewer denoising steps. And this is exciting because you can kind of think of the number of denoising steps as the amount of compute that you use or the wall clock time essentially that you need in order to generate a sample. And so this was very, very exciting for me. It was for the first time we were able to kind of like match the quality of an autoregressive model at a relatively small scale. But that really got me excited, and that and a few other results kind of like show that indeed it can compress the data really, really well. And it got me excited about this technology. And so I've been working towards scaling these models up. So I started a company called Inception AI, where we've been scaling up diffusion language models. We've turned the first commercial scale diffusion language models. And what we've seen is that these trends indeed continue to hold as we increase the model size and as we improve the quality of the data, and we do all the tricks that you would need in order to get a high quality language model at the end. And here you can see a little demo of how the model works for text generation, or code generation. You can see on the right that if you ask the model to generate a function for LLM inference, you can see that this diffusion approach, where you iteratively refine the full object, doesn't take a whole lot of iterations to complete, and it can be, in this case, 5 times faster than what you would get if you were to go through every single token in an autoregressive way. And what we've seen is that these diffusion language models are really high quality, so they are comparable in quality with some of the best models out there, including speed optimized models from frontier labs like Anthropic and OpenAI, and they are significantly faster, like 5-10x faster than autoregressive models of similar quality. And so in particular, we're able to get diffusion language models that can have upwards of 1,000 tokens per second, and we can do it on NVIDIA GPUs. And these kind of speeds you would typically only ever see using specialized AI inference chips. The model works really, really well for code completion. It was benchmarked by Copilot Arena for autocomplete. This is an academic benchmark where humans are able to evaluate the quality of different kinds of code generative models. It's like an ELO score kind of thing where developers see 2 completions and then they vote which one they like more. And turns out that completions obtained with a diffusion language model that can use context to the left and to the right not only are the fastest, you can get them very, very quickly, but they also rank number 1, tied with a few other models for quality. So really high quality completions in very, very quickly. And so, yeah, this is kind of like a summary. I see that I'm out of time, but I hope I convince you that although so far most generative models for discrete spaces have been auto-regressive, there are ways to get diffusion models to work on discrete spaces like text and code. This is very exciting because it enables much faster generative models. There are other benefits like controllable generation, the fact that you can use context to the left and to the right, which are pretty exciting as you think about different applications of these models. And it's no longer the case that the quality doesn't match what you can get with autoregressive models. We've shown in the academic papers that it matches autoregressive models at relatively small scales. And even if when scaled up, the trend continues, and these models are actually very, very competitive with some of the best models out there. And they're starting to challenge the autoregressive dominance that we're seeing today. And that has been true for a while. And so I'm pretty excited about this direction, and wouldn't be surprised if in the future we're going to see diffusion models as being the unified paradigm for generative models, including single kind of generative model that can handle all the modalities that is going to be based on diffusion. I think that's entirely possible. These models seem to be better in many different ways, and so I wouldn't be surprised if that's going to happen. And I'm very excited about keep pushing the frontier of what's possible in that space. And I think I'm out of time, so I'll maybe stop sharing, and I'm happy to take questions.
Thank you, Stefano. So we did receive actually questions that you might have already expected. So will diffusion model be replacing autoregressive model?
I think it's possible, yes. It's too soon to tell, but all the data points are kind of like pointing in that direction. At the end of the day, it's all going to be an inference game, and the architecture and the approach that is more efficient in terms of speed and cost per token is going to dominate. And what we're seeing is that diffusion language models are better suited for parallel hardware, GPUs, TPUs, NPUs, and so I'm very bullish about the future of diffusion language models, especially think about device, like on device, kind of like on edge, kind of like applications, like the kind of things that I think are quite important also for Samsung. I think I'm very confident that we're going to start seeing more and more of these models being deployed on the edge.
How soon do you expect that will happen?
I think there is a little bit of a gap, but I'm a couple of years. I think it's already starting. I think we're seeing more and more applications, especially latency-sensitive applications of LLMs, where diffusion models are the best approach so far. And so as we continue to scale up, more resources are being poured into this technology, and we're seeing other labs are starting to do this. There is Gemini diffusion, there is a diffusion language model from ByteDance. So I think this direction is picking up speed. And as more researchers work on this, it's still very young. There is still a lot of low-hanging fruits, so lots of room for improvement.
Do you see any obstacles in the path?
Well, it's been, it's taken me many years to figure out something that works. Like it's not been easy. I think obviously there's been huge amounts of capital that have been invested in autoregressive models, and there's been a good amount of also co-design between hardware and software. But I think it was similar also when I think about back in 2019, where we started working on diffusion models for image generation. The field was dominated by generative adversarial networks. Industry labs spent a lot of money optimizing that approach, and still the more parallel approach, the more algorithmically advanced solution eventually won. And so I think that's possible that it's going to happen here.
So you said this was a challenge for you to apply diffusion to discrete data, discrete space. But why not we actually apply to continuous space, like embedding space?
Yeah, that has been attempted, including by some of my colleagues at Stanford, Percy, and these staff have written one of the seminal papers in this context. It's been challenging to make it work in practice, and I think it has a lot to do with the fact that the encoder and the decoder need to be very, very precise, and especially kind of like you need to be able to really, really precisely sample from the diffusion model if you want to obtain inputs of sufficiently high quality to be able to decode them back into text that is meaningful. And so while the approach actually works, it's not been easy to make it go really fast because of these challenges at inference time. So I think it makes a lot of sense. Like if I think about reasoning, for example, it's much more natural to do reasoning in a latent space. Like I don't think it makes any sense for LLMs to output these giant reasoning traces that are never actually consumed by a user, by a human at the end of the day. And so I'm very bullish towards more latent kind of reasoning approaches where indeed there is going to be test time compute, and you want to be able to adapt the amount of compute that you apply based on the difficulty of the problem, and you want to have these kind of architectures where you can decide how much you want to refine your answer. But I think there are cleaner ways to do it than the current reasoning approaches. And I feel like diffusion is a very, very clean way of thinking about trading off compute for quality. And so I'm pretty excited about seeing diffusion reasoning language model, which is something I've been also working on, and hopefully we'll see some of that coming out soon.
Okay, so looking forward to bright future of diffusion LLM. Thank you, Stefano.
Thank you.
Okay, so our last but not least speaker is Professor Ben Zhao from University of Chicago.
Great. Thank you all for having me. It's been a great set of speakers today, and I think it's quite interesting that I'm scheduled as the last one. Probably it's a good way to wrap things up. I think you guys have all heard a lot of different, very different approaches and perspectives on generative AI. My perspective that I'll talk about is probably a little bit different from, I think, everyone else here. So in particular, I've been a faculty member since, I think, 2004, so it's been 21 years. And much of it has been spent working on security and privacy issues. For, I don't know, close to 10 years, I think I was working in ways to protect AI systems from adversarial attacks and building defenses and so on. But in the last few years, really my work has sort of taken a different turn. So I'll get into it. Let's start. There's been obviously a lot of excitement about what generative AI can do, lots of different interesting applications, despite the fact that there's some limitations today, a lot of different ways and new ideas about what you can do with generative AI. But with any sort of technology, right, and we've seen this in the past, with any technology, there's always misuse and abuse, sort of the other side of the coin. And for generative AI, I would say that it's a little bit different from some of the prior technologies, whether it's internet or social media, in the sense that some of the harms are more dramatic, but also the impact, some of the negative impacts of generative AI go far beyond the actual users of generative AI. They impact users that have no interest or are not benefiting from generative AI, which is quite a bit different from most technology shifts that we have had in the past. So my point here that I want to talk about today is that it's really important to consider the possible misuses of new technology that we develop. In particular, I think that, as researchers and as companies and so on, we are really ultimately responsible for the outcomes of the technology that we create. And so that accountability, that responsibility falls on people like us. For example, in the context of AI agents and generative AI agents, there are some potential downsides to allowing AI agents significant autonomy on the internet with our credentials. And we have to really focus on how to try to address some of these issues before deploying large scale systems. So, much of my work in the last few years has really focused on image models. So I'll sort of start there. In terms of just generic harms, I think we don't have to look very hard to find downsides of generative AI. So whether it's AI slop taking over the internet, flooding, publishers and news articles and the internet in general, or it's people's, faces, voices being taken without their consent, being models sucked into models and then used, like a skin. But it gets worse. Things like models that produce non-consensual adult images of children, sometimes kids in schools and so on, using chatbots and LLMs to basically commit criminal acts. Mimicking the images and the voices of loved ones, for example, to extract money from the elderly. Lots of these things are happening in real time. And some of the worst things that you can imagine, building deep fakes of models that personalize image models based on celebrities or popular people that we all know and recognize, actresses and so on. And occasionally you'll find a guy in there, but generally speaking, they target women and young women. In this case, this was a lightweight LoRa that was targeting specifically all members of the U.S. Congress. In other words, the legislative, the government body that that makes laws in the U.S. So there was a deep fake model on basically producing images of each one of those government-making bodies, and of course, young women, as is the case. So these harms are actually here today, and this is very different from sort of security work that I've done in the past, where you talk about sort of imaginary risks and potential problems that may come. Unfortunately, these harms are literally real and in front of us and happening in real time. So oftentimes this is not something that people talk about, but this has been the focus of my lab since basically the arrival of really popular generative AI, roughly speaking, mid to early 2022. So today I want to very briefly talk about, not a lot of time, so I'll talk about some of our key protected projects that try to protect human creatives from generative AI, and I'll talk about some of the open challenges and open projects that we're working on. So, I think one of the challenges with understanding harms of technology is that we oftentimes think of them as abstract things, right? So what I want to do is I want to start talking about a very concrete individual person. This is just one example that I know, and I can name many, many other examples. But this particular person is an artist named Kelly McKernan. Kelly, I've known for several years now. She's a friend, and she actually agreed to let me use many of her images from her past. But she is, a prototypical sort of independent artist in the U.S. Okay, so we have images of Kelly when she's growing up as a kid, even very, very young, chalk on a sidewalk, drawing and sort of learning very basic artistic skills, but already showing talent. Young Kelly getting into galleries and really maturing in terms of the type of art she's able to create, and then eventually becoming a professional independent artist, having created an entire style that is uniquely hers. She becomes known for it, and she's able to actually support her family fairly well. So just very briefly, in the US at least, something like more than 50% of all visual artists are self-employed. I think this actually is a understatement. I think the real number is somewhere around 85%, if you take away things like sculptors and gallery curators and so on. They don't get paid a lot. The majority of artists earn barely minimum wage or the poverty line in the US. So they're typically very, barely holding on and paying rent and mortgages, but mostly because they love what they do. So they don't want to sort of switch careers and do something different. Right. So this is Kelly's website. You can see some of her art. This is, even more sort of successful, quote unquote, commercial artists like Carla Ortiz, another friend of mine who's done a lot of work for Disney, Doctor Strange, Black Panther, Guardians of the Galaxy, all these movies. She still does not make the kind of money that we imagine professional artists would actually make. So, having a lifestyle like this, one day, Kelly wakes up and one of her friends tells her that her work on the internet has been scraped into a model, into the first generative AI model as part of Layout 5B. Okay. So what does that mean? That means that very quickly, Kelly learns that you can go on some of these models and basically use her name like a prompt. You can create images that mimic her style, mimic her art, simply by using her name as a prompt. Right. So these models are ultimately mimicry machines. So they're very good at taking input and generating things that look similar to it. So the actual large image on the right is Kelly's actual art, and all the other images are basically copies. Similarly, you can see this type of mimicry actually works quite well across different images. There are lots of images here that basically you can't really tell which ones are real and which ones are mimicries. So there are now industries, there are now platforms where basically tens of thousands of people host these type of models that target individual creators, individual artists. They take art from a particular person. They say, I really like this person's art, but I don't want to pay them to buy their art. So what I'll do is I'll take their art, I'll produce a lightweight model that basically mimics their art, and then that way I will distribute that art, and all of us can enjoy their work for free. Of course, what the actual side effect of this is that the artist who you target basically loses their job and livelihood and ability to make a living. So impact on real human artists. These are people that I've gotten to know. These are really famous artists worldwide. Greg Rutowski is in Poland. He is one of the most famous sort of fantasy artists. But he is also the most famous artist known for being used in generative AI. His name is regularly used hundreds of thousands of times as Midjourney prompts to generate images that copy his art. This is Jean-Baptiste. He is a artist in France, and he has sold lots of his art, done work for Disney, etc. But now he sees mimicries of his art sold online with his name, and then also submitted to Adobe stock images. Basically, people making money by producing art that tries to be his, but with, of course, they're fakes with his names attached. Okay, and there are lots of this. These are just two single examples, but many more artists who are basically losing their livelihoods because you see other people who are selling tons of pretty images, AI generated images as art, but they're producing this art, quote unquote, at 30x the speed that it would take a normal human. Okay, and lightweight LoRa models are basically not only being used to generate revenue for those who use it and take away from artists, but they're also used as weapons online to threaten and bully artists. So if you don't like a particular artist, you can tell them that, you better shut up, or otherwise I'm going to take my LoRa and train you into a model. So lots of disruptions. You can go online and you can sort of see there's tons of social media posts about different types of artists who are suffering from this sort of impact. Many of them are leaving the industry altogether. Many of them are under severe mental stress and depressed and so on and so forth. And then there are other downstream effects, like art schools in the U.S. are closing at a ridiculous rate. Just in a span of about 3 months, in the summer of 2024, several art schools, art colleges that have been around for more than 100 years have closed, all within a span of 3 months, mostly because their enrollment is dropping. Young people no longer want to go into art because they see their heroes and mentors lose their entire livelihoods overnight to an AI model. So they drop out. And when they drop out, these art colleges sort of fall apart and end up closing their doors. So even the ones that don't close their doors are oftentimes closing entire departments because they have to somehow survive and try to make the finances work. Okay, and it's not just art colleges; it's art galleries. It's other types of sort of businesses that have to do with art. They're all sort of suffering downstream consequences of this generative AI effect. So let me talk briefly about what mimicry does, and I'll talk about exactly how we deal with it. Mimicry, you can think of the inside of a diffusion model as sort of a high-dimensional space. But once it learns a bunch of images, it will say, for example, define a certain area as Picasso. It will define a certain area as Jackson Pollock, and then be able to generate something that if I want a painting about Picasso, it'll generate something like that. Now, if you train it on something like, Carla Ortiz, then basically you're going to be able to generate something that looks like Carla. Okay. So what we did was we developed a tool called Glaze that basically disrupts AI using AI. We target AI models and say, well, we understand how these AI models work. We are going to confuse them by slightly modifying the images in very subtle ways so that the images don't look like they're there where Carla really should be, but in fact shifted away in the feature space. So now what that means is that when you ask for a piece of painting from Carla, you get something that looks like a Jackson Pollock, an abstract painting. Okay, so the math, I'm not obviously going to go into that, but it's fairly straightforward multi-constraint optimization. Okay, so here are some examples, and one of them is the original, and the other one is the Glaze version. And so as you can see, the two versions are actually quite similar. We've had artists complain to us that, in fact, it's actually quite difficult to tell the Glaze version from the original. So we have to be very careful about naming files and output so that the artist can tell which one is the original, which one is the output, so they can act accordingly. More sample images. This left columns are the original art from Monet, Van Gogh. Nathan Folks is another artist friend. The middle two columns are mimicries of their art. As you can see, they're fairly similar, not quite similar, not quite good, but similar enough. And then once they've been protected, you can see that the mimicries generally fail and fail badly. And they give you very different artistic styles. So since Glaze was released in 2023, about 2.5 years ago, it's been downloaded close to somewhere around 8.5 to 9 million downloads across 160 countries. It's been sort of adopted by numerous artist associations and groups across the world: South America, Asia, North Africa, EU. Lots of awards here and there, and we've been able to sort of speak to lots of different organizations and even help craft legislation and laws about how to regulate and build transparency and accountability into AI. But turns out mimicry is not limited, of course, to individual artists, right? So if you look at companies like Nintendo, you have characters that everyone recognizes, but you can also see how Nintendo characters, for example, can be taken, they can be trained on, they can be generated, and now you can basically do things like build entire worlds that look like Nintendo characters, but it's actually a different company. So as it turns out, Nintendo recently has actually gone ahead and sued Pocket Pair, the company, one of the companies that has been mimicking Nintendo's intellectual property with generative AI models. And of course, there are other lawsuits as well. Disney and Universal most recently sued an AI firm, Midjourney, for copyright infringement. And in fact, I think just a couple of weeks ago, Warner Brothers, another major movie studio in the US, filed another lawsuit against the generative AI company, also Midjourney. So here, what we actually can offer is something called Nightshade. Nightshade does what Glaze does, except instead of changing artistic style, we can actually change the composition, right? So you take the original photo of a dog, we can add a very barely susceptible sort of scene visible small pixel set of changes. The modified version is very similar to the original, but to an AI model that we target, it actually learns that this dog has these visual features, right? It actually looks like a cat. Now, what this does is that once you do enough of this, we can make these sort of attacks, if you will, much more convincing than the originals, so that once you trained on some of these images, the model starts to get very confused about what these things are. So, for example, you start with this is SCXL, one of the big diffusion models, and you start with these clean images: dog, car, handbag. And I want to make them cat, cow, toaster, cake, and so on. So once we start adding more and more of these samples through fine tuning or actually injection into the pipeline, you'll see that these models will actually become very, very confused about what car actually means. Maybe car means something like this, and dog means something like this. Okay. So again, Nightshade is a tool that we release for free for artists to use and also companies, because the idea is, this is not something that is a weapon. This is something that's more like a defense. Artists and companies who want to protect their images can apply this to their own images, and as long as they're not being trained on, it's fine. But if they are being trained on without permission, without consent, then these altered changes will have an effect on the models. Okay, so I want to very quickly talk a little bit more about other types of projects that we have going on. So first of all, I think a lot of people have seen what we're doing with Glaze and Nightshade and other similar kind of systems. There are now a growing number of research projects that do Glaze-like things, except to protect human voices or music. And there are other ongoing projects that I'm aware of from a number of different universities. But we're also looking at sort of, other issues in this space, right? Generative AI models are going to be around. And when you're training models, when you're fine-tuning models, the fine-tuning process actually makes it quite easy for someone to take an existing model and perhaps basically, act as if it's theirs, right? Because I've sort of modified this model. I can give you a model. You can't tell where I got my model from. So this makes it actually quite challenging. This idea of a company comes around and says, look, I have this model and it's mine and it's great and it's trained ethically from scratch and you can't prove otherwise. So whether you're a regulator, whether you are the owner of a model that they trained on, you would like to understand where this model came from. So this idea of model provenance is something that we're working on right now, which is given a model, given some set of base models, right? So here are some base models. You have a particular model. You'd like to know where this model came from. Is it actually trained from scratch? Did it come from one of the existing models? If so, which model did it actually come from, right? So we're using statistical methods. We're using diffusion feature analysis to actually understand, basically generate fingerprints and models in such a way that we can actually identify, statistically speaking, where a model came from. Was it trained from scratch, or was it actually a modified version of something that was already there? We're also working on other things. Actually, a couple of projects that we're actually collaborating with Samsung Research on. We're building tools that disrupt abuses use of generative AI. So I'm sure you guys, like most of us, have heard about undressing apps that basically overlay images or modify images of people with versions of themselves, perhaps without clothing. But also deep fakes models that target individual people using their photographs. So we're working to basically develop and understand how we can build tools that protect human photos in a way that disrupts these types of abusive applications of Gen AI. And then finally, we're working on LLMs now, trying to understand how to prevent LLMs from leaking private data. LLMs obviously train on a large variety of content. They will train on anything and everything, including user input. And oftentimes, when you're interacting with LLMs, you can feed it content that might contain private information, for example, phone numbers, addresses, loved ones' names, and all sorts of details. So how do we actually protect ourselves from LLMs that might regurgitate content? How do we make sure that this type of data, sensitive data, does not get repeated by an LLM to a different user or to a data record or to an AI agent somewhere? So there are lots of sort of broader applications beyond personal privacy, but this is something that we're actually actively working on. Okay. I realize I might have been talking a little bit fast, but that's my talk. So I'm happy to pause and take any questions.
Thank you very much. So I appreciate your efforts and work to protect artists' copyright. One stupid question. What about the artists that whose work is already online?
Yeah, so of course, right? If you're a long-established artist, many times you have tons of art that's already online. You can't go back and prevent some of them from being stored in the Internet Archive. But for the large majority of artists who are making a living, they actually refresh and maintain their own art galleries on a regular basis. So one thing that has surprised me is how willing these artists are to, in the efforts to go to protect themselves. In fact, many of them, basically, every time that we release a glazed version, an update for security purposes, for robustness, for quality purposes, there's a big surge of downloads, and lots of artists will take down their images, reglaze using the new updated version, and then repost. And a lot of artists now today are actually seeking platforms that give them more control over their art so that they can renew this type of sort of protective protection, right? So it's not perfect, but the protection that we're able to give is actually quite substantial. And so the artists are pretty thrilled with it right now.
So this kind of leveraging adversarial attack on this style transfer, denoising, and so on. So I wonder whether this is a permanent fix to the problem or just temporary. Because somebody may come up with deglazier, right? So to deform the style transfer that you made, and then somebody else can also train with those kind of deformed data.
That's right. Actually, many people have tried. It's been 2.5 years since Glaze has come out. There have been 4 papers, I believe, that have been published on methods to try to attack Glaze. I'm happy to say that most of them have been fairly unsuccessful. The most recent paper combines 5 different sort of adversarial attacks. It takes quite a bit of time on industry-grade GPUs, and you get about a little bit less than 50% success rate. So obviously, over time, this is going to be a challenge, and we keep sort of updating the tool to make it more robust. But I think overall, it really is one tool in a toolbox. We're actually working with legislators in multiple states in the US right now to create AI legislation for accountability, for transparency. So that has to happen, but also, there's lots of legal cases that are moving forward, sort of redefining what is correct and what is legal in terms of training, in terms of acquiring content. And so I'm hopeful that, right now these tools are protecting artists in the short term, but hopefully in the long term, we're all going to evolve into a more equitable licensing model where AI can coexist with artists. And some of these tools will not be as critical or as needed as they are today.
Okay, that's a good point. Regulation has to catch up here. Okay, so you talk about the image most of the time, but what about the language? So how to protect the authors of novels and those kind of documents? How can you protect them?
Yeah. I've been answering this question for quite some time. As you can imagine, it's the threat is a little bit different because writers tend to not be quite as recognizable in their artistic style, in their output, right? So, I would say it is rare that you can identify an author quickly using their words, right? But I think there are other threats. The fact that generative AI can generate books or what look like reasonable books, but are not terribly deep or meaningful, but it can generate books at a very, very high speed, right? And so right now, if you go on the Amazon ebooks market, you'll see the entire marketplace is flooded with AI books. And that is the problem for real human authors because it is now much more difficult to reach a publisher and for their human books to actually stand out. It is difficult for human music to stand out on things like Spotify and some of the other music platforms. So detection and separation, identifying what is human made and what is AI is a bigger problem, right? But yeah, we're also working on things like how do you keep secrets? How do you remove sensitive data from LLMs? Unlearning is a method, but it's very fragile and doesn't quite work like people hope. So we're trying some alternative techniques that solve the problem.
All right. Thank you very much.
Thank you very much.
Okay, so this concludes our morning session for today. So thank you all, the speakers and the audience who have been watching with us. In the afternoon, we are coming back at 1 p.m. With the talks that Samsung researchers have prepared. So we hope you stay tuned and enjoy the rest of the sessions. Thank you.
Welcome back. Our first speaker of session 1 is Sang-ha Kim, Corporate Vice President and Head of AI Productivity Team at Samsung Research. Please welcome Ms. Kim.
안녕하세요. 오늘
Good afternoon. I'm Sang-ha Kim, Vice President of Samsung Research. Today, I would like to talk about TrueBench, a framework for evaluating generative models in productivity scenarios. So this is my agenda. As AI has been adopted across industries, there is a growing number of cases showing improved efficiencies and creation of new values.
금융 서비스를 비롯
From financial services to healthcare, logistics, manufacturing, automotive, and robotics, AI is being used very widely. However, the ways AI is applied and the benefits expected may vary depending on each industry's characteristics and requirements. Selecting the optimal AI model for a company's needs is not easy. Generative models often produce multiple plausible answers rather than just one single answer. And there's the lack of consistency, and producing reproducible evaluation is very difficult. As a result, a variety of benchmarks are now being developed to improve characteristic model behavior. However, many public benchmarks focus on general language ability and abstract reasoning, making it hard to judge whether a model will meet the diverse requirements and complex scenarios of real productivity tasks. In addition, public benchmarks tend to suffer from data contamination over time. So, leaderboard numbers should not be taken at face value. It's difficult to trust these numbers. Therefore, moreover, because many benchmarks are created primarily in English, they offer limited visibility into multilingual performance. Most are implemented as a single-turn test that measure only one-shot responses, which means they provide little evidence about behavior in real settings like chatbots. Consequently, strong scores on these benchmarks do not guarantee the expected performance. To address this gap, we developed the TrueBench, a benchmark for selecting models on real business tasks. We prioritize enterprise-relevant use cases, verifies whether models satisfy all stated requirements, and employ reliable, reproducible evaluation methods that minimize subjective human judgment. So we wanted to create a reliable evaluation approach. So, for example, users may sometimes ask a service to draft an email in a simple, free-form manner, but it's also common for the system to require the model to fulfill explicit constraints in order to perform downstream functions. And to deliver these services reliably at the same layer, the model must produce outputs that satisfy those requirements. So the following requirements must be satisfied by the model. Beyond explicitly stated requirements, many tasks may also hinge on implicit constraints, the background assumptions, domain conventions, and safety rules that are not spelled out but must still be satisfied. So to perform the tasks correctly end-to-end, a model has to infer and comply with these latent constraints as well. Accordingly, we analyze real-world requirements and voice of customers, prioritize 10 essential categories, and build input data sets by decomposing tasks into 45 subtasks. We also produced data in 12 major languages, including Korean and English, in collaboration with professional translators and researchers at overseas institutes to evaluate models' multilingual performance. So we have also drafted an initial checklist for each input, then used an LLM to validate whether that checklist could accurately assess the model's responses. We evaluated along 3 dimensions: correctness, sufficiency, and minimality, and it's iteratively refined the checklist based on those evaluation risks. So as I've said, correctness, sufficiency, and minimality, these 3 dimensions test will be carried out, and we have repeatedly corrected the checklist. Using the finalized checklist, we evaluated each model output against the input. If all requirements are satisfied, the sample is marked pass, and if any requirement is missed, it will be marked fail. So it's going to be either pass, or any single missing will cause failure. This mirrors the strict constraints in real production system, and by enforcing an explicit rubric helps reduce bias in LLM judged evaluation. So we wanted to create a clear guideline to minimize bias issues. So this automatic pipeline is now published in Hugging Face leaderboard. Through this site, you will be able to look at the leaderboard of TrueBench. So on the site, you will see 10 category descriptions along with the representative sample data sets for each of those 10 categories. Because of the concerns over data contamination, we have decided to provide just the sample data sets, and 10 categories and 45 soft tasks. We have visualized all the information, and by checking the category scores, you can see what kind of characteristics the model has, which model is strong for inference, which is strong against hallucination or for safety. And through the leaderboard, you can measure the multilingual performance for 12 languages. So including 12 languages, including English and Korean, we can analyze the model's performance for key languages, and we provide these visual services. Beyond model quality, we also assess response efficiency. And the dashboard provides a distribution plot for performance versus response length of number of output tokens. So as you can see on the screen, we provide the distribution graph. For response length, we report both the median total output tokens and the median tokens for the final answer segment, enabling apples to apples comparison across models. Through this, we can we can measure the efficiency of the model's response. And if you go to this site, you will see submit button, and you can submit the model with your chosen performance tuning parameters and run the evaluation, and the results are reflected on the leaderboard. To prevent indiscriminate testing, there are submission limits per model and per organization. And after we extract the evaluation results, the results will be reflected in the leaderboard, and the entire process is automated. As I've said, to prevent indiscriminate testing, we have limits per model and per organization, and only users belonging to the model's Hugging Face organization may submit. And once you enter the site, you will be able to see the ranking by TrueBench. There are open rate models that are already evaluated, and you can check their ranking. In Samsung Electronics, we have in-house generative model, Samsung Gauss 2, and through TrueBench, we have carried out their performance evaluation. When we opened Gauss 2 last year, the current category performance now has been improved. And on the left-hand chart, you can see that we are continuously improving the performance, and the right-hand chart shows the language performance evaluation. TrueBench was also used to check the Gauss evaluation, and when we compare this to others, we can check that TrueBenchmark has evaluated our Gauss 2 in comparison to other open models, has excellent functions and performance, as you can see on the right-hand chart. When you look at the number of tokens and quality, the quality was great for response. And through this, when compared to publicly released open weight models, Gauss 2 shows superior performance considering quality relative to output token length. And our future plan, we are going to create a lot more detailed tasks to identify the optimal models for various use cases. And we are also going to expand the category to accommodate complicated agent task execution capability. So this link that you can see on the screen will take you to the TrueBench's overall leaderboard. That is the end of my presentation, and we have received some questions beforehand, so let me answer that question now. First is, using the current LLM, how can we identify the gap between LLM technology and expert productivity who's not familiar with LLM technology? There could be 20, sometimes more than 20 points based on benchmark, meaning that when you're answering within orchestration, based on response logic, even if it's the same model, the performance can vary greatly. Second question is, when new up-to-date data is needed for law and medicine, do you have any know-how to reduce the hallucination? Hallucination sometimes creates difficulties in being used. Hallucination is not all bad, though. As you know, when you are creating creative work, some level of hallucination can enrich your content. But as you have mentioned, for law and medicine, you would need fact-based, precise answers. And in this case, in generative AI, hallucination is an ongoing task that we need to tackle. Of course, we try to reduce it, and by having a more refined and precise prompt, we can improve this, and we can also do a lot of search and retrieval of more fact-based information and give that to LLM to refer to, so the LLM can refer to more fact-based information in answering. And in the process of answering, they can also check the reference information. By adding the reference, we can reduce hallucination and make it more productive. Third question is, does Samsung also have SLLM for each device for training? Actually, Samsung has models of different size, and when we are implementing this based on the MPU of the product, we carry out additional optimization and quantization. For After introducing LLM-based productivity tool, what kind of feedback have you received? In this case, there were two key cases. As I've mentioned before, TrueBench. Before that, overall benchmark usually perform the single term based performance and then apply this in dialogue or conversation based services. So therefore lacking in guarantee for multi-term. If you're using tool here, when the tool misfunctions, that could be a problem. And second is when you're asking and giving the answers to users or services, there is a gap. Users sometimes, as long as you give the answers that humans can understand, they will be able to cover any flaws. But in the service, you have to give a clear answer and based on facts and clear formats. Fifth, LLM-based productivity tool is used in various fields, but for time, resources, and securities, there are limitations or constraints. Can you give us any case studies for reflecting those constraints? For security, because of the security issues, they sometimes use on-premise board or use it on orchestration make sure that there is no security issues in calling the LLM. And for time and resources, GPU resource serving or other efficiency can be resolved through model sizing or quantization that will accelerate the speed or reduce the use of resources or reduce the number of GPUs used after office hours. Number 6, what kind of AI functions do you think your functions can be differentiated from other AI? Samsung Electronics has a lot of workflows, and our Gauss understands that better than others so that it can better understand the workflow in and outside the company, therefore recommend us to the best tools. Generative AI performance itself is important, and orchestration is also important so that the tools can be called right in the exact time it is needed. And we should try to reduce hallucination so that we can provide more accurate information. That is the focus of our research area. So that concludes all the Q&As. Thank you.
Next, our second speaker is Michael S. Brown, Vice President and Head of AIC Toronto at Samsung Research. Mr. Brown, please begin your talk.
Okay, so greetings from Canada. So I'm calling you right now around midnight my time. So let me talk about camera and AI white balance. So when you take a photo, we often think that what you see on the screen is exactly what's in the physical world. So you look with your camera and what you see through the screen is what you see with your eye. But your camera actually has many processing steps that are applied to produce that image on your screen, right? This photo. And we call this a pipeline because these steps are applied one after the other, and it just continuously does this while you're looking at the image. So today what I want to talk about is one of the most crucial steps on your camera is known as white balance. So white balance is a very simple step, but if you don't get it right, your image won't look good. So this is very important for your color in your image. So let me just give you an example. So if you look here, if I was to change the white balance, you would notice that the image changes and you get what we call a color cast. And this is not desirable. So it's very important to make sure that your auto white balance is correct so the image color looks correct. So what I want to do today is explain to you, why do we need white balance? Why does the camera have to do this? You don't have to do it as a human. You're not white balancing, but the camera needs to. And then I'll tell you how we can use AI to do auto white balance for cameras. So to understand white balance, we actually have to first understand a little bit about color. So when you look at a tomato, you just look at it and you get this sensation, oh, that's the color red. So let's think about, how do you really do that? So in the physical world, there's no colors. The tomato isn't red. The tomato is actually reflecting electromagnetic radiation. So the physical world is full of electromagnetic radiation, from gamma rays to X-rays, ultraviolet, and there's a certain range that's known as the visible spectrum in terms of wavelengths. So when you're looking at a tomato, you're not looking at the color red, you're looking at its reflectance of the spectra. So you could imagine that this tomato reflects spectrum, the visible light spectrum, like this. So we call this a power spectral distribution. Now that comes into your eye, and your eye has 3 cells that act like sensors. And we call these the short, medium, and long cone cells. And these respond to different electromagnetic radiation differently. So the short one responds to this region, the medium this region, and long this latter region. So what happens is, when this radiation comes into your eye, these cells respond and you get these sensations. So the short one responds a little bit to this region because there's not much radiation there, medium a bit more, and long even more. And that produces this sensation of red. Oh, I see red. Now, cameras have similar mechanism that mimics the human eye. So what we do in cameras is we put these filters on top of the pixels that are somewhat like the short, medium, and long. Different sensors have different filters. So you can see they're not perfect. It doesn't exactly match the human eye. And so that means that the sensor will perceive the color of the tomato slightly different. So what we can do is, in the factory, we can calibrate that sensor and its response to the incoming light. And it's not very complicated. It's just a simple 3x3 linear matrix that you can calibrate that takes the sensor response and maps it to human perception. But we haven't really seen the whole story, because what is this reflecting? So here I say, well, the tomato is reflecting light like this, but what about the light? So what you're really doing is you're looking at the tomato under some illumination, let's say sunlight or indoor light. And that illumination has its own spectra. So actually what's coming into your eye is the reflectance of the tomato reflecting the environment lighting. And so you don't actually get this into your eye, this spectra here, you get a slight variation on it based on the lighting. Now what's really interesting is you can observe the tomato under many different lighting conditions. Sunlight, different types of indoor light, even you'll see sunlight changes. So noon versus dusk versus dawn will be slightly different. Now the question is, does it change how you perceive the tomato? So I would think that all of you agree that when you look at a tomato, it always looks red. So you have an amazing ability to correct for this. So your visual system compensates for this different illumination. And this ability to see objects under different illumination, but as the same color, is known as color constancy. Now, this has been well known for many years, and there's a mathematical model called the von Kries transform. So what Johann von Kries figured out was, somehow your brain, working with your eye and its response to long, medium, and short, can figure out, determine what is the environment lighting, and it divides that out. So it's just a simple division. If you have some lighting, you kind of detect what the lighting is, and you just divide out that lighting, so you correct for any different lighting. And I'm going to do an example. So this example is from Andrew Stockman. He's a very famous professor who works in human perception, and is this very nice example to kind of demonstrate color constancy. So what I want you to do is I want you to look right at this point, and I'm going to count to 10. But what I'm going to do is I'm going to show you a different image. So keep looking here. Look right at the same spot, and I'm going to count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when I go back, this image should look more constant. Now, if you close your eyes and maybe look away and look back, you'll realize the image actually had, let me just go back to another slide. You can see that it had this color cast in it. So by just looking at this, this is kind of mimicking the color constancy ability in this demo. Now, the problem is cameras can't do this. So your camera, when it sees a tomato under different illuminations, it actually has the color cast in that image, the sensor image. So we have to correct this, and this is white balance. Now, sometimes in the academic world, we would call it computational color constancy. So if we get this correct, then we can remove this color cast, and so the image will look, the colors will look correct, and the colors of things like tomatoes and skin tones will be proper. Now, how does white balance work? Well, the first thing you have to do is, given this sensor image, you have to detect what is the overall illumination. Once you detect that color, you can correct it. So this is essentially the von Kries transform. So we apply von Kries transform to every image that comes into your eye. So that's white balance. Now, if we think about the problem, the challenge is actually this part. How do you detect the illumination? So the pipeline, your auto white balance is do illumination estimation, you get out the color from the sensor, and you divide it out. But if I give you just a general image, and I say, here's an image, tell me what is the illumination. It's not an easy task. And you have to do this no matter what type of image you're looking at. Now, digital cameras have been around for a long time, so there's lots of examples of auto white balance. But what I'm going to talk about today, and these are different methods, and some of these methods we still use, but of course, everything's moving towards AI. AI right now gives the best results, so I'm going to talk to you a little bit about AI methods. So again, this is the processing chain for auto white balance. The image comes in, you estimate the illumination, and then you correct it. So essentially what we're going to do is we're going to replace this with some sort of neural model, an AI model. Now, before we start, we should think about how do you get training data for this, right? We need to supervise this model. So one of the things we have to do when we work on AI white balance is we have to capture training data. So we tend to go outside and indoors, and we take a camera, and what we do is we place these charts, we call these calibration patterns, inside the scene. So we know that these patterns are white, but because of the color cast, we know that this is incorrect. So whatever this white is reflecting, that must be the illumination. So we go in and we manually click on these regions to get the ground truth of the illumination for that image. Now, the problem is, if you don't mark this out, your AI network will learn to detect where the color chart is in the image. So at training time, what we do is we actually mask out the region that has the color chart in it. So when we train, we do validation, we do testing, you have to feed it images that mask this out. Now, the very first successful AI white balance algorithm came out in 2017, and this was done at Microsoft with one of my old colleagues, Stephen Lin. I was really just starting up, especially the deep learning AI. We had these convolutional networks. So what this team did is they took the AlexNet, one of the original very successful deep networks for images, and they cut off the end and they modified, we call the head of the network, to predict the illumination. And if you look at what the network actually learned, it learned how to identify in the image regions that were reflecting light. So it tended to learn where the white regions in the image were. So here you can see it's learning, oh, this region here looks like it's very a good predictor of the illumination. This region here, this white shirt, is a good predictor. And it also estimated local illumination. So when you combine these two, what it thinks is local versus the region it thinks is white, it's a very good predictor for the actual color of the illumination. Now, the problem with these early generations, and this is one of the first papers, there were many, the problem is that the networks were just too big. So the networks tend to be 500,000 to 5 million parameters. In fact, I was just at a conference earlier this year. I saw an example, and it was 25 million parameters network. Now, that may be small compared to a large language model, but remember, this is something that's being applied to every image that's coming in, right? You have your video, you're moving it, so we have to do this very quickly. So even 5,000 parameters, or sorry, 500,000, 50,000 parameters or 500K parameters is too much. So we need lightweight AI models to do this. So I'm going to talk about two papers that came out of our lab that work on this a problem that tried to give lightweight AI auto white balance. So the first work that we looked at was called this two-camera illumination estimation. And what was happening at this time, and now we're all very used to this, is our cameras have multiple, or our smartphones have multiple cameras. So we wanted to use this fact that we have more than one camera to be able to do the white balance. So I'll show you the basic idea. Now, remember, you have two cameras, you're looking at the same scene. Now, the camera sensors on your cameras are different. So one of your cameras, maybe your wide angle, will be one sensor with one set of spectral sensitivities to light, and let's say the telephoto will have a different spectral sensitivity. So that means even though they're looking at the same scene, in this case the tomato, the colors of those two different sensors are slightly different. Now, under the same illumination, you can compute a transform that tells you how to transform this sensor into that sensor in terms of color. The color, this is just like how we calibrated the camera earlier. Now, what if I change the illumination though? Well, if I change the illumination, because these sensors are all slightly different, that transform will change. So now we see that the transform between these two cameras is related to the scene color, and it's also related to the illumination. Now, this observation was made almost 20 years ago in a little bit different context by Graham Finlayson. At that time, though, first, smartphones weren't very popular, and smartphones only had a single camera. So we realized we could use this observation to do it for modern cameras. So again, what we're exploiting here is that under different illuminations, this simple 3x3 matrix, so 9 parameters, is encoding up the change in the illumination. That means that these 9 parameters can be used as a feature to a neural network. So what we did is we developed this system that took 2 of the cameras, we would turn them on at the same time, we would align them. So this, let's say this is your normal camera and this is your telephoto, or this is, sorry, your wide angle camera. We would crop out the region, we would downsample them, so the images are very small, and we would very quickly compute this transform that aligns these 2 images in terms of color. Now, this transform, 9 parameters, is what we feed into our neural network. So our network's very, very simple, but it's very good at predicting the white balance. Now, to be able to get the training data, we needed to be able to ground truth these images. So we built this little setup where we put a color chart, a calibration pattern on this pole, and we would go out and take images. So this would be your main camera at the wide angle, and I know it's a little bit hard to see here, but you can see this is the color chart, and here's the color chart. Same here. So this gives us the ability to ground truth, to know what the illumination is in both of these images. Now, what we can do is when we apply our algorithm, we can compare it with many existing white balance algorithms, including some of these early white balances I mentioned to you, like Gray World from like 1980. Now, when we do the comparison for white balance, what we do is when we measure the illumination from the ground truth, you can think of that as a vector in RGB space. So when you estimate your illuminant, the error that we typically measure is the angular error. How different are these 2 vectors? If the angular error was 0, that means you're 100% accurate. So what you can see is compared to all of these methods, our 2-camera white balance method gave the best results. But what's even more interesting is our network is so simple that we only had 200 parameters. So compared to these other deep networks that have, 500,000 to 5 million parameters, we only have 200 parameters, and we can do this very quickly. Let me show you one other example, or another work that we did in our lab. and this is known as time-aware white balance. Now, the observation here is that at different times of the day, you're more likely to see different types of illuminations. And so what you're seeing here is the illuminants up here in these little circles. These are outdoor illuminations like sunlight, shadows, and these are indoor illuminations. So for instance, right now for me, and one reason I'm a little bit tired and speaking slowly is because it's midnight. So at midnight, there's not much outdoor illumination. So this gives us a lot of information about what we're likely to see. So what we did is, in addition to the neural network, we also keep the time of day. So under noon, the same environment. Under sunset, the color illumination will be slightly different. So let me explain a little bit more about time of day. So when I talk about time of day, you just think about the sun coming up and going down. And you can see here that the sensor response to this different type of illumination will be slightly different. So it's not just the clock time, it's also related to your location. So at 7 p.m. in July, if I'm in New Delhi versus Toronto, I'm going to have a different sun profile. So maybe one's going to be dusk and the other is still going to be the sun's high in the sky. So what we do is we take not just the clock time, we take the geolocation and we convert that into a probability of the type of condition, dawn, sunrise, and so on. And we had to capture a data set that also had this information in it. So we had to capture a new data set that has this time and geolocation. And then what we do is we still use the colors as a feature to predict the illumination, but we also embed in the time. And not surprisingly, what happens is, again, using angular error, we get some of the best results. But what's really nice is because we have this additional feature, we have a very small model, only 50, in this case, 5,000 parameters. So very good performance, only 5,000 parameters. And in this case, we don't have to turn on two cameras. We just simply look at the time and we look at the geolocation. Okay, so white balance, I hope you understand it a little bit better. It's a critical step that you have to apply for every image that you take. And if you don't get it right, the image colors will look incorrect. And I talked about two methods that came out of our lab here at Samsung in Toronto, where we looked at ways we can use additional information to have very lightweight AI white balance methods. Okay, so thank you very much.
Next, our third speaker of session 1 is Cheun Lee, Master of AI Model Team at Samsung Research. Mr. Lee, the stage is yours.
네, 안녕하세요.
Hello, nice to meet you. I'm Master Cheun from Samsung Research, and our team has been working on GAUS, our own large language model. And recently, we have paid special attention to knowledge distillation, KD technology. So today, I want to talk about the areas that we have reviewed for various knowledge distribution technologies, and then what kind of strategy can enhance and maximize the performance of your models by installing KD technologies. This is my content. I will first talk about what knowledge distillation is and what needs to be distilled and how we should select the source models and data, and what is the most efficient way to use the resources for distillation. Last but not least, how we can utilize knowledge distillation. Briefly, let me go over the definition of knowledge distillation. So there is a great large model, and with that teacher's model, we can train the students' models. That's what knowledge distillation is. The ultimate goal is to create better training signal. So I have prepared 3 images here. These are AI generated image. On the left-hand chart, the student is reading the book by himself. Next to it, there's a teacher face-to-face teaching the student. Last but not least, there are some implicit ideas the teachers have in her brain, and if that can be conveyed to the student, it will improve the efficiency of learning. So the technology that is matched to three areas would be label distilling, logic distilling, and feature distilling. So let me take a look at the label first. So that is generating the teacher model output and using that for training. Second, logic, it is to distill probability distribution at the token level. Compared to label distillation, this will deliver not just the next word, but the teacher model when it predicts what was the level of confidence with which it was predicted and what are the probability of other words being predicted. So it provides much richer information, therefore making the learning more effective. Last but not least, the feature-based distillation. This looks at the internal representation of the teacher model and distill that to the student model. For each layer, output representation or attention heads, attention map can be used for distillation. So let me compare these three areas. So there is a trade-off between effectiveness and efficiency. Label is simplest and most effective and efficient. It can create training all at the same time. Its implementation is very easy, but for logic and feature-based distillation, the student model and teacher model should have the same architecture. So there is a restraint for these models. So if we don't have to select one out of the three. NVIDIA has announced Minitron, and after pruning the model, distribution can improve the pruned model's performance. And as you can see, embedding loss and encoder block output LM head, these 5 types of loss can be combined to train the model, and various combination can add other losses and improve the efficiency of the performance. As for loss function, usually the teachers and students output, there is the care divergence that needs to be minimized. Teacher models and teachers' probability can be the target, or students' number can be the target, and that will determine forward KLD or reverse KLD. There are various research about this. Some research says that forward is better. Other research says reverse KLD is better. In our case, we have tested this on our own. In general cases, forward KLD proved to have higher performance. So let me now talk about teacher model. Selecting the best teacher model is really critical for knowledge distillation. And if you only want to create small models, but you might need a large teacher model, which requires a lot of resources for training. But logic distillation or feature level distillation requires teacher and students have same vocabulary and similar architecture. And the training data should also be similar to make the distillation most effective. So if the vocab is different between the models, can distillation be possible? Let me introduce you to related research. And you don't necessarily have to always go for the highest performing teacher models. Teacher model, when it creates the output, it can effectively do the inference based on certain technologies. This is when the vocabulary between model is different. This is about large distillation. Vocabulary is different. Tokenized And then sequence might be different, so logit level matching would be impossible. Sequence is different and probability distribution is different, cannot be matched. In this research, tokenize must be done first to create different sequence and create chunks that can be aligned for two, and chunk can be created that aligns the two models, and there can be probability calculation at the chunk level, and with that divergence, training can be done. Even if the vocab is different, other additional signals can be extracted, which can be helpful. However, logit-based distillation is better and it requires far less amount of information, so it's not going to perform as well as other models that have the same vocab. This is a similar research. This shows not the chunk level probability, but it looks at the teacher level probability and calculates the tokens. Compared to logit level models, this is less effective. Next, with the same vocab shared between teacher and student, when teacher has been trained and when student has been trained, when the distribution is different, distillation effectiveness can be low. And we did the test ourselves, and after distillation, student model used mixed languages or unlimited iteration. Hard label training models can sometimes be overconfident or underconfident. So compared to other training, it can do temperature calibration for distillation. And in selecting the teacher, computer optimal teacher must be selected. Distillation scaling law research shows that cross entropy loss of the student model and tokens quantity and teacher models cross entropy loss, it is defined as the function of these three. So when you plot that, you will get the graph on the right. This shows the amount of resource that you have, size of the student model, and the amount of training. And this can identify the expected loss. And you can come out with compute optimal teacher based on this data. One interesting here is on the left lower chart. It shows the teacher's loss is a denominator. This shows that teacher model's performance doesn't have to be the best to be most helpful. Teacher model's performance and student model's performance, when the gap exceeds certain level, then after distillation, the performance can be lowered. And as you can see, the effectiveness can be degraded. In selecting the data, you can do it in a distillation effective manner. Mini PRM research shows that teacher models probability and its student models probability to define the characteristics of data for sampling. For example, teacher models probability is similar or larger than student model's number, then student model can follow the teacher model very well. So this can be a relatively easy data, so you can do downsampling for this kind of data. However, on the opposite case, teachers' probability and the students probably have a big gap, then student will not follow the teacher effectively. So you need to consider this as a diverse and complicated cases. So in that case, you might want to upsample the data to increase the effectiveness of learning. And for distillation, teacher model, student model, when they have a big distribution gap or performance gap, teacher models generated data can lower the efficiency of student model. But for on-policy distillation, it uses the data that student has created, and you put the logic from teacher model on top of that for training. We have actually tested this, and student models performance, if it's not high enough, then student models result itself will have low quality and did not have any advantage for performance. To apply this technology, it is important to make that students' performance achieve certain level, or you can do one sample, select one sample out of many. The best scenario here is teacher model and student model's output should be combined in the optimal manner. According to speculative KD, it got the idea from decoding. For areas that is relatively easy, we can follow student generation. When there is a big gap between the two, teacher models generation should be followed. So based on this approach, we have been able to combine and blend the student and teachers label in an optimal way. We have done that, and this showed the highest level of performance, and teacher and student showed the highest similarities for distillation. Next, when multiple inference is done, since this is based on sampling, you could see that some output has low quality while others had higher quality. After multiple sampling, you can use reward model to select the best model, and with that data, training can be done to achieve the highest level of effectiveness. The biggest drawback here is compared to multiple sampling, relatively little data is actually used for training. Right-hand chart research shows that you don't have to always select top one. You could go for lower ones to improve the model's performance continuously. Here we have actually done the research ourselves and released that on ACL. When training on-device small models, we use a lot of knowledge distribution technology. Small models require multiple training. Sometimes hyperparameter learning is needed. And in this case, if we have to calculate logit separately, this requires just too much resources. So teacher model logit is inferenced and stored once, and we used offline distillation. The entire number of logit was too big, and we could not have all the storage to do that. To store one token, these days, models vocab is between 10 to 200,000, which requires huge amount of storage. So we cannot save all the tokens for all the logit. We did sampling, and spots offline distillation technology was used. So we did not go for the top angle. We followed the teacher's distillation and then looked at importance sampling-based sparse logits. So 12 out of 100,000 logits per token was good enough for us, and storage requirement was reduced by 3,000 times. Last but not least, I want to talk about how knowledge distillation can be used efficiently. I want to introduce you to some applications. The most important application would be to enhance the performance of the models itself, especially for smaller model performance. Gemma 2 and Quen 3, these are also used. We also have Gauss model for on-device and Gauss model for cloud. On-device model, we use the knowledge distribution on cloud-based Gauss models. As you can see on the right-hand chart, overall performance has been improved consistently. And after pruning the model, KD was used to improve the performance of the pruned model. Minitron model, after distillation, had model architecture change, therefore the performance could decline. So it's important to have the same level of output as the original model, and knowledge distillation can provide the additional training. And there are many cases when we have to inference, and speculative decoding is on the spotlight. Multi-token predictor or draft model training can also use knowledge distillation. For draft models, we need more than just high functions and performance. We need the original to have a similar distribution, and knowledge distribution can be very useful in this case. Conclusion: most of the model vendors might have the similar challenges. Knowledge distillation can be used for training variety of models, especially small models training. Recently, we are seeing Agentic AI and related models are being launched in large numbers. They are also used for cloud and on-device. So on-device small models can sometimes have to be highly performing, and this will increase the demand for knowledge distillation. And knowledge distillation can be used to save cost. That is not wrong. However, based on our experience, for effective distillation, teacher models sometimes need to be built, and teacher model need to be inferenced for data retrieval, which is a very costly process. So knowledge distillation technology itself should not be used for cost saving. It can be used to maximize the performance of small models. So that is the end of my presentation. Thank you very much.
Next, we are pleased to introduce the last speaker of Session 1, Joohung, Master of AI System Team at Samsung Research. Mr. Hung.
네, 안녕하세요. 삼성.
Hello everyone. I am Han Myung-ju. I'm from Samsung Research. The title of my presentation is On-Device, Unlocking On-Device LLM, especially the devices that we can use for the household goods. On-Device LLM, well, not only theoretical research is being done, but also in your own goods and product, it's now being embedded. And in order to do that, Samsung Research has been doing a lot of research, and I'm sure they're utilizing on-device LLM, how you can actually utilize it. So I hope my presentation can be useful. Let me begin my presentation. So in order to realize on-device LLM, how we do that, what's the level of that, let me tell you, and also how we can actually apply that. Not only we stop there, but also there are many steps that we have to undergo. And internally, we provide diverse services. Last but not least, on-device LLM, how we can implement that, what kind of software we need. We provide software as well, and I'd like to introduce the software that we can use as well. What is on-device LLM? Well, inside the device, LLM is now being deployed. So inside the device, when the device is implemented, then we can use the data, private information, especially the data that cannot be released to outside. You can get service, and also using the resources inside the device, you can use that. So although the internet is not being connected, you can do that. So there's no delay or no lag time. You can get all kinds of services that you'd like to enjoy. Such a great LLM, when it's on device, where can we actually use that? What kind of service are we entitled to use? ChatGPT or other services, I'm sure that you use that a lot. And LLM is not built just for the ChatGPT, right? If it's just for the purpose of using ChatGPT, then definitely you can use that. But we didn't create on-device LLM for that purpose, but rather for a server, there were things that we couldn't do so. But using on-device LLM, we can actually use all kind of services. For example, let me explain what kind of services people can use. You can see on the left, it's a now brief. So the users recommend the schedules, or there are services that users can use, and the sleep quality or the health based on the data. The device can provide services recommending certain behavior or certain things. Not only that, like a news article or telephone conversation, or if you attend a certain lecture, the contents can be summarized and then can be provided. And definitely interpretation and translation using on-device LLM, you can enjoy the service. The quality is far better than the existing one. And also the reply is really automatically produced with a high quality. From the simple model using on-device LLM, it understands the context and also even the patterns, speaking patterns, and the way the users respond, it can mimic that. So not only text-based service, but also the photos can be searched or documents can be identified. Anything that are inside the device, it can be used. Not only what I'm showing you now, but also there are other areas where it can be used. So not only the mobile phone devices, but in other product, the more LLM application is now being used. So on-device LLM, for that, Samsung Research is doing a lot of research, and let me introduce on a high level. Definitely, during the previous session, you heard about a small LLM model. Yes, we need to create that so that it can be embedded on device. And it doesn't mean that a small LLM can definitely create an application, because each application has its own task to carry out, and we need to modify or we need to orchestrate that. And definitely the app developer, they can easily acquire the usage that they would like to use. And based on that, depending on the usage, we can come up with the on-device LLM, but also we need a memory, latency, and throughput. In order to implement this in a software, of course, you had a big device, but in order to use this in on-device, you need lower memory, lower latency, and high throughput. To customize that as well, we are trying to develop a better on-device LLM. When you have such engine, the data needs to be input, and also we need to provide a foundation. So these are the framework. So if I compare that with the server, this is LLM to be implemented within the server. So Samsung Research is doing research on that so that LLM can be deployed. Among them, let me introduce the first thing. What we are trying to produce is on-device LLM. It's a small language model. Let me tell you what's the current level. So it's on device and the language model, starting with the Galaxy S24. With the name of the Galaxy, we are providing the service. And it's operated based on the small LLM compared with our competitor. You can see that Gauss on-device model, the parameter number is about 4 billion. It's less than 4 billion. It's around more than 3 billion. So I'm comparing that with our competitors, and their language model is much, much larger. So when we compare our small language model with the language model with more than 4 billion, the performance is actually better. And about 6.8 billion model, when we compare, the performance is not lagging behind at all. So with much smaller language model, but on par or better performance, we provide service at a much quicker pace. So on-device model, in order to compress it, the parameter numbers need to be maintained. However, the capacity needs to be compressed further down, or we call that as a quantizations. So one parameter has a capacity of about 4 bits, but now we are going further down and we are moving toward 2 bits. So we are doing research so that we can compress further down. In a very aggressive way, we are carrying out the quantization. In the future, we believe that the on-device LLM, the size will be by halves and then the performance will be double. And LLM, if that wasn't that burden, then we hope to realize far better performance with the same speed. That's our expectation. So such a great compressor, high speed, on-device LLM, even if we have that, what if we cannot embed that in our device? The post-process is extremely important. We need several steps. We call that as each developer to develop not to develop their own model, but we provide one service with the app developer. Without having a full understanding of the model itself, they can provide the service. So the service is critical because on-device LLM, a small language model, has very unique features compared with the large language model. Especially the language model on device is compressed to 1/100th of the actual large language model, which means that the high speed or high performance cannot be on a par, which means that computing is quite challenging. However, as long as we give the right prompt, then the work can be done. But it's quite challenging, especially in order to ask the small scale LLM to do a complex task. Sometimes the speed or other process cannot be well done. Another feature is that the memory is very small compared with the large language model. So the context, the length is very much limited. Under such circumstances, on-device LLM, in order to use that, we call fine-tuning or additional learning process. In order for the on-device LLM to do additional learning, we need to create a task data set and then let this small LLM to learn about that. But to do that, we need fine-tuning. For example, when we use LLM, there's application. If there are more than 20 applications on mobile phones, we need 20 variable or 20 different LLM. It doesn't mean that we cannot install 20 different LLM. So what we do is we just embed adapter, and using LoRa method, we do that. And creating LoRa, well, for the app developer, it's quite difficult to do so. So we provide it as a service. Through fine-tuning, when adapter is deployed, I'll share with you one example how effective it is. Samsung Health message, when it's being produced, the prompt is well done. So in a short summary, important message is given to users, but small language model, when instruction is given, you can see that it's in English. Even though we ask the applications to send the message in Korean, it is written in English. So the instructions we give needs to be complied with. In a simple manner, we hope to generate the message in a short format. Not only that, there are many other work or tasks that can be done on device. So app developer needs to do that. And as a one service, we provide that. Here, prompt engineering is included. Prompt engineering looks like very simple things to do so, but unless you have used LLM for a long time in an expert way, it would be quite challenging to utilize prompt engineering. So a semi or quite a bit of the automizations can be possible, and also each engineers need to create its own data sets, and it's very expensive to create data set one by one. So a small data set needs to be augmented to a large data set. We provide such a service. Definitely, as I briefly mentioned, the fine-tuning, additional learning can be done, and quantizations, yes, it's quite challenging work. And starting from the prompt engineering all the way to the quantizations in a one pipeline, all the services provided automatically. And using the models and devices, it's being distributed. The test and evaluation is done as a service. So under the name of the AI Studio, using web server, we provide to the outsider. Unfortunately, this is not provided to outsider, but inside the Samsung Group, we provide this service. So using this, even though the software developer, you don't have the LLM understanding, you can easily and quickly create this and then use it. Last but not least, when LLM is created, when the adapter is created, how can we adapt that to our household goods, including mobile devices or fridge or anything? What kind of software we provide? Let me share that with you. Starting from here, it's an open source, which means that you can use this even though you are not a member of the Samsung Group. The first software is NN Trainer. It's Apache license, open source, and not only Samsung Research, but developer outside Samsung are currently developing this. And then Trainer software is using the data inside the device, and then the software teaches learning large language model to learn. So robot cleaning devices or air conditioners, they ask the AI to learn additional information so that they can provide more suitable services to the users. So compared to the solver, a very small or minute software can be installed, and using that features, we are installing on-device LLM with a much smaller software. And definitely because of that, the LLM can be operated in a much faster way. Here, I'm showing you a demonstration video, and Galaxy 25 3 billion parameter, yes, is now being used. As you can see in this video, 3 billion model, but still at a mobile phone, the result is quite fast. And the memory is not that huge in your mobile phone, but still you can see that if you look at the memory usage, it's merely 1.3 gigabytes. And the model size is about 16.5 gigabits. And as you can see, about 10 tokens per 10 seconds, that's the performance, is now being shown. And in this image, NPU and GPU is not being used, only CPU is being used. Still, the performance can be used. And well, even if you can use the total of the 16 gigabytes with the same computer when there's a limitation, then the speed is not that different. About 15 to 13, there's a mere differences. And the speed of the writing the sentences, there's minor differences, but from the beginning to the end, it's actually much more efficient. The reason why this is possible is because all the context is not written there, but it tries to identify what is really necessary. The model software understands that, so it does scheduling, and then it upload what's important. It's not necessary, then it get rid of that. So in a very extreme manner, in a very fast manner, it does that. What you are looking at right now is for the laptop. So LLM on laptop CPU, it uses other framework. The speed is like double faster. Going back to the original purpose, LLM is more fine-tuned for the user's perspective. You can use it with the personal data. And even though it's the same task, so it's 6 stack, 8 multi-headed encoder, and then trainer use 420 MIB. So additional learning is possible. Another project I'd like to share with you is it doesn't do the LLM, but rather inside the device, it's a software that replaces, and TV or other household goods uses this software. Companies outside Samsung are co-developing this. They use this software for their products and services as well. And then Streamer, as you can see here, is currently providing services for 8 gigabits and API and data for LLM and the model for LLM are all distributed and being used. Let me tell you the takeaway of my presentation. It's written in one page. Samsung Research for LLM, we are developing model, about 3 billion parameter model, but also at different purpose, different sizes. We are doing a lot of research for the LLM, and so that it can be applied. In order for these LLM to be used for a product, even though you don't have understanding about LLM, we are trying to provide services with the software that you can use it. And each devices, in order for this software to be implemented, we are providing the service in an open sourcing way. And there are other software that we have not disclosed yet, but we plan to provide at an open source. So you can take this open source software, or you can take part in developing it. Especially in November, Linux Foundation will be hosting open source summit, and NN Trainer, NN Streamer, and other AI software will be presented. There will be a workshop. Please join the Linux seminar and then share the information with us. That concludes my presentation. Thank you.
welcome back. Our first speaker of session 2 is Kuntal Lee from AI Productivity Team at Samsung Research. Please welcome Mr. Lee.
안녕하세요.
Hello, good afternoon. I'm Lee Gonzalez from AI Productivity Team at Samsung Research. I am now developing Deep Dive, which is a deep research report generation services. And today I would like to talk about multi-agent orchestration technology that we used. I will first talk about multi-agent and agent orchestration, and then talk about the results of Deep Dive report generation. When we are doing research in-house, we have to research huge amount of data, and sorting the data out requires a lot of time and effort. Especially identifying the source of data and separating in-house data from external data requires laborious and backbreaking work. And sometimes it leads to duplication or loss of data in the process. If somebody can do the research and identify the key points, the user will be able to focus on more added value work, and that was the motivation behind the research report creation services. This service will enable the usage of various documents home and abroad and inside house and outside the company, and provide the research output in a format the user wants. Going beyond the LLM's limit, AI agents can now use the tool to plan and adjust to the circumstances. They can not just answer the questions, but also automate the problem resolution and workflow automation. AI agents can use LLM as an inference engine for planning, uses variety of tools for action, and review the results, update the action, or update the result. Deep research report is not just an answer to a question. It goes through search, analysis, sorting, generation. So it cannot be defined as an LLM call alone. We wanted to automate this, and we have decided to use AI agent. AI agentic architecture can use one outperforming agent or have a team of multi-agents. In using one agent, we can develop the services easily, but for dealing with more complicated problems, as we have to use more and more tools, then agent might have a hard time deciding which tool to use for which circumstances. And it can only do one work at a time, so it is not fit for simultaneous execution of various tasks. So we wanted to break one large problem into smaller problems and make each agent focus on small agent and try to introduce multi-agent. Constructing multi-agent can be done in various ways. It depends on how the team can be organized. Orchestrator worker pattern is one commander orchestrates everything and team members follow the command. The strength is efficiency and consistency. Peer-to-peer pattern has the team ones collaborating on an equal basis, which is good for diversity. Hierarchical is like a multi-level organization with a mid-level leader. Each layer will focus on the given task, and it is good for unpacking complicated problems. There are various ways to combine the multi-agents, and it depends on selecting the right agents for each subject area. So let's look at the characteristics of multi-agent orchestration for deep dive. We wanted to imitate the human's research process and determine the direction of future humans' research direction, and we came up with 3 stages: plan agent, and then research agent executing the research from various perspectives, and then report agent will output layer for generating the final output. For research agent, we have built sub-research agents so that there can be parallel processing of various information. And you can never predict the results of a research. So it's important to have an interim result check so that it can always go back to the previous stage to revise the research plan. Let's take a look at the characteristics of each agent in detail. First, plan agent. Plan agent is for planning the execution of research, depth of research, and approach for research, and also decide what other agents need to do. For example, sales reports for 2025, when there is such a request, plan agent will determine the goals for research agents. First, extract the financial data. Second, identify the market trend. Third, identify the factors that affect the sales. Fourth, to go through the overview of businesses of subsidiaries. So output agent can write the report. Let's look at the inside of plan agent. Plan agent, when it receives a research request, in order to identify the goal, will refer to the previous history data or the source that need to be inferred. Plan agent is a tool that can have access to the previous history, dialogue, and research. And it will establish its own plan and allow the users to intervene to make up for the deficiency in the plan. Such plan will be checked to see whether it's okay for research process and then pass the work to the next agent. Next, research agent. When plan agent breaks the large topic into subtopics, then research agents will ask various questions to find the answers from variety of sources. Such questions are researched in parallel, and the result of the research will be combined together. And if there is need for more research, then additional research can be done, and that information will be refined so that research insight can be identified for smaller research topics. In the output stage, the output of the research will be printed out to express the value of the research. When there are multiple outputs, that the report will be very long. In that case, consistency of context and format would be very important. So multi-agents can be configured in a sequential manner to maintain consistency and reflecting the style document requirements of the users, then using the memory, the initial output requirements of the users will be reflected in the final output, and the output can be printed out in various platforms. Next is multi-agent orchestration, the three key areas. First, human in the loop. Human in the loop is when plan agent plans for the user's requirements, will try to clarify the unambiguous questions from the users to come up with clear requirements. Users will usually enter just the research topic they're interested in instead of asking detailed requirement questions. So the plan agent will play the role of a guide in making the plan more precise and clear. Deep research can use human in the loop, which is a very important process. Next is RAG, used in deep dive. RAG is a critical information to give facts in LLM's response. Deep dive can retrieve from various sources, so orchestrating the query would be really important. Query manager will be used to identify the queries for each characteristic of the source, and adaptive RAG has been used, and the queries should not duplicate but mutually offsetting. Vector keyword-based hybrid search has been introduced, and multi-vector retrieval has been used to search various formats of documents. And when using the extracted information, the source of the information is added to add to the trustworthiness of the response. Next, let me talk about context engineering. Context engineering allows the multi-individual agents to continue to follow the context by refining and managing the information. With the multi-agent, the context for agent will be enriched, so each agent might have a confused as to which work has to be done. So context should be managed, and model's context size is limited, so noise must be minimized, and necessary information need to be developed into a structure to develop the information for the next agent. Context engineering is for generating the research that combines the research from various research agents. The research plan can be expanded into various queries. Each research agent will end up having huge amount of information, and that information needs to be turned into insight for the research purpose. Research at the subtopic can be summarized and refined according to the research topic, and then output layer agent can print out the output based on the goal of the research. Next, let me talk about multi-agent structure application case in printing the deep dive service report. Deep research users are created to conform to the complicated requirements of the users. It can orchestrate the depth of research, and it can classify the requirements based on the depth of the research. So even if it's same topic, it can come up with long reports, shorter reports. This is huge amount of research report, and if you want deep research, it requires more time, but it can come out with huge amount of research output in a consistent manner. In terms of the word pages, it can create as many as 30 pages of output. Research agent, when it concludes the research results, the source document can be maintained to identify the source of the data at a sentence or paragraph level, and users will be able to find out whether the model has created the data or it has been quoted from other research data. Not just for the documents, it can also create infographic reports. Such charts, tables, flow charts can be included in the infographic report. It can also output slides for presentation. And audio style reports can be generated, so people can just listen to the report instead of reading them. And mind map format will allow you to understand the structure of the document easily. Conclusions. Today I've talked about multi-agent orchestration for generating deep research reports. As you have seen, multi-agent has the architecture that is appropriate for creating the output for complicated research. And for optimum quality and performance, we have to find the right way to combine these agents together. And we'll continue to specialize in individual agents, expand our tools so that we can create better report generation services. I hope you can positively review the possibility of introducing multi-agents in your research and services. Thank you very much for your attention.
Next, our second speaker is Han-jae Kim from AI Productivity Team at Samsung Research. Mr. Kim, please begin your talk.
Hello everyone. I am Han-jae Kim from Samsung Research. I'll be talking to you about Document AI Universal Document. In this presentation, I will introduce what Document AI is and the detailed components, technologies that make up Document AI, and also show the document analysis result of the model we have developed. First, let me begin with the introduction to Document AI. Document AI can be defined in various ways. As we see it, Document AI refers to a technology that acquires diverse information within documents through document processing and then delivers this information to an LLM to generate answers. The goal of Document AI is to contribute to improving internal productivity by reducing the amount of the time users spend searching for information. When we defined problem and began developing Document AI, one of the major challenges we encountered was diversity of internal documents. Internal documents are not limited to text-only reports. They also include invoices in table format, Excel sheets, PowerPoint slides that contains graphic information such as image and chart. Understanding unstructured documents can be viewed as understanding three aspects. First, identifying what the components of the documents are. Second, determining where those components are located. Third, and lastly, understanding the relationship among those components. In particular, since documents often contains both text and image information, it is essential to also consider the relationship across different modalities. From these motivations, we have summarized what we believe constitute a successful Document AI, and there was a question previously delivered to us, so let me tell you about the answer first of all. I have shared with you the result, and also I told you that we'd like to enhance the productivity. So forcefully, instead of standardizing all the documents, it is important to develop the algorithm that can be applied to different methods, and that should be the Document AI direction. So that's what we are currently trying to develop. So here, what are the successful Document AI? Let me summarize what are the successful Document AI. First, as mentioned earlier, optimized analysis models are needed for various types of data that documents can contain. Second, in order to improve productivity, lightweight network models are required that can process large volumes of document quickly. Finally, an information processing procedure, specifically a chunking strategy, is necessary for effective multimodal data retrieval and interleaved generation. To achieve these three objectives, we have designed the following end-to-end flow. When document is input, it is parsed in short time through three lightweight models. The data is then chunked. Relationships are inferred, and finally, a retrieval generation process is performed to enable question and answering. From next slide, I will explain our parser framework. To achieve these three objectives, we have designed the following end-to-end flow. When document is ingested, it is parsed within short time using three light-weighted models. The data is then chunked, relationship are inferred, and finally retrieved generation is performed. There was a question, and using one VLM, we can do the parsing. Well, we have considered that direction as well. As a result of our analysis, using one integrated VLM, it's far better to use more quantified small sub-model, light-weighted model in terms of the accuracy, in terms of the processing speed. Therefore, OCR, layout detector, and table recognizer, which are the models they use to conduct document parser. Let me take a look at one by one. First, OCR. Since internal documents exist in multiple languages such as Korean, English, and Chinese, we use OCR models specialized for each language type in order to ensure accuracy. At this point, it is necessary to determine which OCR model a given language image should be processed by. To this end, we develop a lightweight language identifier. This language identifier was trained using synthetic data, thereby reducing the burden of data acquisition. Acting as a router, it directs each language image to the appropriate specialized OCR model, thus enabling accurate multilingual OCR. Now, next is layout detector. Layout detector, well, it is important to understand the layout comprehensions. Layout refers to the components that make up documents such as paragraphs, tables, and image. To identify the locations and type of this layout, we employ layout detector. Well, using annotated documents, the layout detector is trained to recognize the bounding boxes that indicate the positions of each layout element as well as their types. Finally, this table recognizer not only identifies the text inside a table, but also understands the table structure, thereby determining which category each piece of text belongs to. Lastly is a table recognizer. Table recognizer, when a table image is given, table recognizer interprets the table structure in HTML format and by applying OCR to the table image, converts the text into the data that is inserted into these corresponding cells. And that's how we input all the data. So we restructure the table. One of the unique thing is that when the table is integrated or when there's an image inside the table, then when the images are embedded within the table, they are placed into appropriate empty cells to complete the table. The parsing results produced by these models are as follow. This is the paper picture, not only text but also image, and tables are successfully processed with OCR and layout detection. Even when text and image informations are embedded inside a table, we confirm that the table is correctly structured. And we can easily understand what are these, and then the relationship between text and image we can comprehend. From next slide, I will explain data chunking. Data chunking refers to the process of gathering and refining large amounts of information extracted from documents in order to make them more suitable for search and question answering. Therefore, when performing chunking, it is important to test retrieval and generation result in parallel and find the appropriate chunking method. Well, the main challenge here is image. When generation is performed to output both image and text together, it is necessary to determine which text chunks each image corresponds to. For example, in this case, the blue image should be connected with the bottom chunk containing vacuum cleaner reset information. The way this relevance is quantified significantly affects the connection result. Typically, the relevance between the image and the text chunk is measured by similarity. There are several ways to make the determination, using multimodal embedding, projecting both into joint embedding space, and then measuring the distance between the embedding. That could be one way, or using captioning or OCR extracted information from the image to generate text embedding and then measuring similarity between text embedding. By combining multiple similarity measurement method, the accuracy of similarity estimation can be improved. This allows us to quantify the similarity and determine which text chunks a given image modifies or describes. Next, I'll move on to the information retrieval steps, which find information relevant to the user's questions for questioning answers. Similar to how we measure similarity between image and text, multiple search methods are combined to identify information related to the query. The two most common methods are keyword search, which excel at precisely capturing information containing specific keywords, and dense search, which uses embedding to capture semantically similar information even when expressed differently. So we call this as a dense search. Keyword search is effective for exact matches but weak at finding semantically similar but lexically different expressions, and dense search can complement this limitation. Fusion is performed by weighting and combining the search score from each method. Typically, fixed weights are used, but we found that the performance varies significantly depending on which search method is emphasized, which in turn depends on the characteristic of the document. For example, if a document contains large amount of domain-specific terminology, keyword search may be more effective, whereas in cases with many synonyms, dense search proves more useful. Based on this finding, we are developing a technique to adjust the weight depending on the type of information contained in the document. Finally, I'll conclude this presentation by showing you the question answering result generated through the previously described chunking and retrieval process. As shown in the pipeline on the left, we define the data based on the inferred image-text relationship and provide it to the LLM in a way that it can understand. This enables multimodal RAG or retrieval augmented generation, which can generate interleaved outputs of image and text. As shown in the result image on this right, users are able to intuitively view not only the text responses but also relate charts and image together. Such generation results are highly dependent on the inference of image-text relationship. By linking examples image to the descriptive text in each step and delivering this to the LLM, the model can generate text along with the corresponding image that is connected to the text. Through this approach, users are expected to search and analyze complex documents more quickly and in greater depth, thereby contributing to improved productivity within the organization. That concludes my presentation. Thank you.
Next is the third speaker, delivered by Dylan Yeo from AI System Team at Samsung Research. Mr. Yeo will now share his insights with us.
네,
Good afternoon. I'm Yohei Dong from AI System Team. Today, I will talk about On-Device AI Studio, which is on-device AI development environment. First, I will briefly introduce you to why we needed AI Studio and some of the functions provided by AI Studio. So let me first talk about on-device functions and how we came to develop this. In the early days of on-device AI, each feature shipped as its own fully fine-tuned model targeted to a single task. As accuracy targets rose and the number of features increased, model sizes grew and the total storage footprint ballooned. To overcome this, we adopted a design that places a high-performance generative foundation model known as LLM and FM on the device and adapt it per feature. So we have selected high-performance generative foundation model. With Galaxy AI deploying an on-device LLM and FM, something we hadn't done before, has enabled faster and more efficient expansion of AI features. To adapt capabilities on top of an on-device LLM, LoRa fine-tuning was essential. Developers started to define the target feature and then prepared large training sets and then established clear evaluation criteria. They then trained multiple LoRa variants over the data, followed by quantization and runtime optimizations for the models. So the resulting models are evaluated against required quality bars using several methods. When needed, we strengthen the test suite, augment the data set, and reiterate retraining and reevaluating until the feature meets the desired performance. So let's look at the AI Studio functions that effectively enables development of such AI functions. AI Studio first develops the development environment for developers to develop the AI functions they need using generative AI. First, there is Prompt Studio that enables AI function development just with the prompts. And there's the Adapter Studio that supports LoRa training and optimized training pipeline. Last but not least, there's the Evaluation Studio that enables the verification of the adapted results and performance evaluation. First, the Prompt Studio, using a model with far stronger instruction following than the LLM shipped on S25, it lets you build AI features without LoRa fine-tuning. It uses prompting only. Developers can author prompts using prompt templates, apply techniques like few-shot prompting, and see the results right away. Because this approach requires no data preparation or LoRa training, it naturally increases developers' productivity and enables faster proof of concept for a wider range of new AI features. Prompt Studio can also optimize prompts automatically, suggesting versions that perform better on our LLM than the developer's initial draft. So it will enable novice developers to try developing the prompts. Next is Adapter Studio. Because of on-device LLM size limits, many features can't meet production-grade quality with prompts alone. In those cases, developers need LoRa fine-tuning. Adapter Studio provides an automated pipeline to train language and multimodal LoRa on top of a foundation model. It automates the complex training steps and offers progress monitoring so developers can apply a variety of fine-tuning techniques and build adapters easily without micromanaging every details. As I've mentioned before, achieving production-grade performance with LoRa requires an iterative loop, training on large data sets, optimize and evaluate, and then augment the data and retrain to push quality higher. For Galaxy AI, multilingual support means collecting language-specific data sets, and real gains come from high-quality data augmentation. In practice, data quality and coverage determines model performance in many cases. AI Studio automates the most time and labor-intensive part of LoRa fine-tuning, securing high-quality training data. Once developers provide a clear feature definition and evaluation rubric and a small seed dataset, AI Studio uses a large teacher model to auto-augment data, continuously analyze how each augmentation impacts LoRa performance, and iteratively distill the most beneficial examples. Repeating this loop yields curated corpus of high-quality synthetic data tailored to the target feature. When building on-device AI, the biggest departure from server-side adapters is the quantization stage. In Adapter Studio, once adapter training finishes, we run an automated pipeline for quantization and graph optimization. We mainly use two approaches, PTQ and QAT. PTQ needs no extra training and is fast, but some models can suffer noticeable accuracy drops. In those cases, we apply QAT to recover quality at the cost of additional training time. AI Studio automates this flow and produces chip vendor neutral, quantized artifacts that can be compiled for different NPUs and SoCs. Finally, let me introduce the model evaluation functions for AI Studio. For generative models, rigorous evaluation is as important as development. Evaluation Studio supports testing not only text but also multimodal inputs such as speech and images reflecting the input for IoT supported in Galaxy AI. It offers multiple evaluation models, including automated judge with large LLMs and human-in-the-loop qualitative review. You can also track performance through the final quantized on-device model, ensuring that any accuracy shift after deployment is fully captured. That's the overview of AI Studio today. So what's next? We plan to extend our automatic synthetic data generation from text-centric to full multimodal so that Galaxy AI can deliver more user-friendly experiences. We are also working to automate evaluation prompt authoring and to generate test cases that better mirror real usage, boosting perceived quality. Finally, we will strengthen multilingual support, helping developers who are relatively less familiar with cross-language workflows achieving strong results. And this is some of the questions that we have received and about the future of the AI and the long-term direction of AI semiconductors. But these are too difficult a question for me, so I want to answer two of the most practical questions. First, is there a single Swiss Army knife stack for training and deployment? I have used the TensorFlow Lite so far, but we had to run it in specific runtime. The Onyx helps a lot with interoperability. On mobile devices, we use in-house runtime. So the question was single army knife stack for training and deployment. Is there any such thing? We haven't found one yet. For training, depending on the training environment requirements, we sometimes use TensorFlow or PyTorch, and we use various training framework, and then we sometimes change the models. And Onyx is very helpful for securing interoperability, and mobile devices we use our in-house developed framework. Samsung has very diverse configuration environment. We need to run on CPU, GPU, NPU efficiently across many SKUs. Some of the framework we need has been shared via Tizen, but more remains to be released. Our hope is to let you try the Samsung Research AI runtime directly and collaborate on its development. The second question, what is the most difficult challenge for satisfying the user's requirements who are used to using large-scale models such as on-device LLM? We actually don't have a solution for meeting their requirements future. We have clear resource restrictions on terminal, and that is the biggest challenge for us. I would like to thank once again everyone for the thoughtful questions. That concludes my presentation. Thank you very much.
Next, we are delighted to present the last speaker, Sang-Jun Park, from AI Solution Team at Samsung Research. Please welcome Mr. Park.
네,
Hello, I am Park Sang-Jun, who is developing AI voice dubbing services at Samsung Research. Today, I would like to introduce you to various voice models and some of our technology challenges. This is my content. Let me first talk about Samsung Research's voice and sound AI in general. Samsung Research has been developing voice and sound AI technology for a long time. Switching sound and voice and finding the speaker, differentiating the speaker. And with the sound AI, we can separate the source using source separation technology, and these technologies are applied on various Samsung products, mobile devices, and home appliances. Recently, Galaxy AI's interpreter and audio eraser were developed using this technology. And you can open the refrigerator just by saying, open the refrigerator. Individual voice AI models can expand the functions and experience of devices. I'm sure that it's high time that we think about the next step. Using the various voice AI model, we can come up with more user-friendly that has biggest impact on our business. First is to combine various models. Recently, we have combined various voice AI models to develop the services. And for example, we can provide voice assistant technology, and they are being developed into services. And today, I want to talk about AI voice dubbing technology.
최근에
And recently, global video platforms are coming out with so much global content. For example, as you're well aware, the Squid Game, K-pop Demon Hunters are blockbuster contents that are gaining popularity around the world. And YouTube subscriber, Mr. Beast has the largest number of subscribers, 440 million subscribers. Mr. Beast provides individually dubbed content. So global contents are gaining momentum around the world using the dubbing and subtext technology. And voice dubbing market will only grow down the road, and AI's portion is growing as well. AI voice dubbing technology compared to voice actor has a cost advantage, as you can see on the right-hand chart. Voice actor versus AI cost is very low. So it can be done at affordable cost, and we have to think about improving the quality of our technology. So I want to talk about SR voice dubbing technology that can improve the quality of voice dubbing. End-to-end voice dubbing pipeline, as you can see on the slide, combines various AI models from input video to dubbed video. It has end-to-end pipeline. And each AI model needs to function organically, seamlessly to minimize cost and human intervention. This flowchart shows function by function pipeline. And in fact, the model has to make arbitrary decisions from time to time. Like in order to maintain background noise, it has to go through background noise separation. So the background needs to be separated from human voice and then decide whether to stop the background noise or not. So by using various AI models in an intelligent manner, we have to come out with good logics. Each individual models, once the performance declines, what kind of outcome are we going to experience for scene segmentation? And the video will be broken down into scenes. And if that's not done properly, then we will see very large or small context. And when the scenes are combined again, there might be discontinuity. And individual models' performance is important, and overall end-to-end dubbing performance is also important. Today, I want to talk about speech generation, part of this table. When speech generation is flawed, it will create unnatural dubbing speech. And in order to improve this performance, we are focusing on two technical points. First, we try to have human-like natural voices with our dubbing technology. First, the background. When people talk, for background, there's the rich style speech or spontaneous style, as if we are talking in our everyday life. And read style speech will require accurate pronunciation, fixed and repetitive prosody. However, for spontaneous style, the focus would be on conveying thoughts and intents, would be more expressive, and there are certain expressions that like filler, stuttering, a lot of pause in spontaneous style of speech that will make the speech more natural. In order to model spontaneous style speech, we use two technology. First is architecture. In the past, there was very explicit alignment between text and speech. This will lead to accurate pronunciation, but would be less natural. So from given text, we want to do entire duration modeling and then generation of speech. And unlike the conditional way, we do global conditioning of text to come out with more natural voice. And for data, existing TTS use mostly read style data sets, but we try to use spontaneous style data sets as much as possible to achieve human-like naturalness. And then we are also focusing on voice cloning. So when we are dubbing, we are not just creating the voice, but we try to make it sound like the original voice of the speaker by using voice cloning technology. And the characteristics of human voice can be classified in spectral properties and temporal properties. Timbre, pitch would be spectral properties, and prosody, speaking rate, would be temporal properties, which would be more difficult to replicate with voice cloning technology. So we try to introduce in-context learning so that reference speech can be given as a context, and then try to fill up the voice. And we can follow the reference speech by doing this. And data, there will be much more data. We are using hundreds of thousands of hours of data to express various properties of voice. Using this technology, we have created a voice cloning sample, and I will play this for you.
Forum 2025 Are you having a good time? I hope so, because we worked very hard to make this tremendous, really tremendous. Now, this is the last presentation. Don't worry, no more talking after this one, I promise. Just a little bit more energy and you'll make it.
네, 좀 비슷하게 느끼셨나요?
Did it sound like the original speaker? So as I said, this is your last presentation. So I've shared this dubbing demo, but because of the copyright issue, I cannot show you the video, which is very regrettable. Apologies. If you're still interested in our dubbing technology, please let us know, and we would love to share more demo videos and look for collaboration opportunities. So instead of demonstration, we wanted to focus some of the pain points that we are trying to overcome. With dubbing, having a similar voice is important, but there is always trade-off. Accent is part of the speaker's identity. And for dubbing, we need to have cross-lingual voice cloning. And that leads us to decide the accent for dubbing. If the reference speech is in English and it's produced in Korean, what would be the most natural accent in Korean to make it sound like the original speaker? We have prepared 3 samples. The later you go, the similarity will be low, but it will sound more natural. In the first sample, similarity is rather high.
AI Forum 2025. 이제 제가 사실 트럼프 대통령인데요. 삼성 AI 포럼에서 만나뵙게.
I am President Trump, and it's an honor to meet you here at Samsung AI Forum. I'm President Trump. Nice to meet you here at Samsung AI Forum. The last sample sounds like any elderly man in your neighborhood. Sounds very natural and familiar, but sounds less like the original speaker. So we have to find the right trade balance, which achieves the best sweet spot for customer experience. Second point that we are trying to tackle is to decide what to dub and what to keep. Basically, we don't have to dub everything. Excessive dubbing would make it less natural. There are sounds that can never be dubbed, like background noise sound effects. We need to maintain original sound for that. And for non-verbal human sounds like laughter, coughs, these sounds can be generated as sound effects, but it's better to keep the original sound. Last but not least, singing vocals. We need to maintain the melody of the vocals, so after dubbing, it might sound unnatural. And songs, we need to keep on the original vibe. For songs we don't dub, we try to keep the songs intact. But other sounds, we try to dub. So for variety of sounds, we have to decide whether to dub or whether to keep. So we need source separation technology and decide how to process each models. Last but not least, this dubbing technology can be used for both B2B and B2C. For OTT partner app companies, when they want to globalize their contents or develop more accessible services, for example, for people with vision disabilities. And there are certain countries that legally require subtexts. And for individual users, video creators are gaining momentum these days, so they can expand their contents multilingual at a very low cost, and viewers will be able to enjoy their contents in their native language. These are some of the potential applications for our technology. So that's all for my presentation. Thank you very much for your attention.
Last, Taeyeon Kim, Corporate Executive Vice President and Head of AI Center at Samsung Research, will deliver the closing remarks. Please welcome Taeyeon Kim.
네, 안녕.
Good afternoon, ladies and gentlemen. I'm Kim Dae-hyun, Executive Vice President from Samsung's AI Center. 2025 Samsung AI Forum. Thank you very much for joining us and staying with us until the very end of this forum. AI has been with us for more than a decade now, but still is under a lot of spotlight. So we have invited eminent scholars in the morning and introduced you to various technology that Samsung is developing. I hope you have found today's forum informative. Before I conclude, I want to mention that Samsung is really dedicated to AI. If you're interested in Samsung Electronics AI, please look for opportunities to collaborate with us down the road. Thank you very much.